Hello there, and welcome to Life Beyond Seen, a quiet place where curiosity slows down, questions linger a little longer than usual, and science is allowed to unfold without rushing toward answers. Wherever you are listening from right now, whether it is late evening, early morning, or somewhere in between, you have arrived at a very particular edge of the world. Not a shoreline you can walk along, not a horizon you can point to, but a boundary that exists far below the surface, where the ocean no longer feels familiar, and depth itself becomes something else entirely. Tonight, we're drifting downward, not in a hurry, not chasing spectacle, but following a gentle descent into a part of Earth that remains almost entirely beyond human reach, the Hadal zone, a region so deep that sunlight has long since vanished, so pressurized that even our strongest machines hesitate, and so unexplored that much of it exists only as empty space on our maps. Is not a place most people think about very often. The ocean, after all, usually ends for us at the beach, maybe a coral reef, perhaps the open sea glimpsed from an airplane window. But below all of that, far below where whales dive and submarines roam, the ocean continues to fall away. Before we go any further, take a moment to notice where you are. What room are you in? What sounds are around you? And what time is it, right now, where you're listening from? It's a curious thing, thinking about the deepest places on Earth while sitting somewhere warm and dry, held up by solid ground. That contrast is part of what makes this journey interesting. If you find this kind of exploration calming, or if you simply enjoy letting your mind wander into places most humans will never visit, you're always welcome to like the video or subscribe. It helps this slow, thoughtful space reach others who might need it too. Now, let's begin gently, not with creatures or mysteries, but with the simple act of going down. The ocean covers more than 70% of Earth's surface, yet most of it remains unseen by human eyes. Even today, with satellites, sonar, remotely operated vehicles, and decades of research, we have mapped the surface of Mars in greater detail than the deepest parts of our own planet. That fact alone is worth sitting with for a moment. There is a place on Earth, right beneath us, that is less understood than another world millions of kilometers away. The Hadal zone is the deepest layer of the ocean, beginning at around 6,000 meters below sea level, and extending down into trenches that plunge past 11,000 meters. To put that into perspective, Mount Everest, the tallest point above sea level, would fit comfortably inside the deepest trench on Earth with room to spare. If you placed Everest at the bottom of the ocean's deepest point, its peak would still be more than a kilometre underwater. One of the most famous of these trenches is the Mariana Trench, located in the western Pacific Ocean. Its deepest known point, called Challenger Deep, represents the lowest known place on Earth's crust. And yet, despite its fame, we have sent fewer humans there than we have sent to the moon. Only a handful of crewed descents have ever reached that depth, each one lasting just a few hours before returning to the surface. Below the surface, the ocean is divided into zones based on depth and light. The sunlit waters near the top feel alive and familiar. Fish shimmer, plants grow, and the rhythm of day and night still applies. Descend further, and the light fades. Colours disappear. The water grows colder. By the time you reach the Hadal zone, there is no sunlight at all. None. Not a trace. This is not darkness like a moonless night or a closed room. It is a complete absence of light, uninterrupted and permanent. Pressure, meanwhile, increases relentlessly as you go down. At sea level, the pressure around your body is 1 atmosphere. At 10 meters underwater, it doubles. By the time you reach the Hadal zone, the pressure is more than 1,000 times greater than what you experience right now. That kind of force does not merely press on objects, it reshapes them. It crushes air-filled spaces. It turns small weaknesses into catastrophic failures. For the human body, this environment is instantly lethal. Even the most advanced diving suits cannot protect a person from such pressure. Bones would not be the issue. The problem is air. The air spaces in your lungs, your sinuses, your blood. At those depths, unprotected, the body cannot survive even a moment. This is why human exploration of the Hadal zone depends entirely on machines, carefully engineered spheres of steel and titanium, designed to keep pressure out while humans sit inside, suspended between curiosity and physics. And yet, life exists there. That fact alone reshapes how we think about what is possible. For a long time, scientists assumed that the deep ocean, especially the deepest trenches, would be nearly barren. Too cold, too dark, too pressurized, too lacking in food. It seemed reasonable to assume that life would thin out and eventually vanish as conditions became more extreme. But the Hadal zone did not follow that expectation. Instead, it revealed something quieter and more unsettling. Life did not disappear. It adapted. Creatures living in the Hadal zone are not visitors from above. They are not strays that wandered too deep. They are native. Their bodies are built from the cellular level up to function under pressures that would instantly destroy most known organisms. Their proteins are structured differently. Their membranes behave differently. Even their enzymes operate under conditions that would render surface life chemically unstable. These organisms live without sunlight, which means no photosynthesis. The base of their food web is not plants or algae, but organic material that drifts down from above. Tiny particles of dead plankton, waste, and debris fall slowly through the water column like marine snow. Most of it is consumed long before it reaches the trenches. What arrives in the Hadal zone is sparse, irregular, and unpredictable. And yet, life persists. Some of it feeds on this falling debris. Some relies on bacteria that use chemical energy instead of light. In certain trench environments where tectonic activity exposes minerals and releases chemical compounds, microbial life thrives by exploiting reactions that have nothing to do with the sun. This kind of ecosystem feels almost alien, yet it exists right here on Earth. When scientists first began to sample the deepest trenches, they expected to find simple organisms, perhaps bacteria and a few invertebrates. What they found instead challenged assumptions. Amphipods, small shrimp-like creatures, were discovered at depths exceeding 10,000 meters. Fish were observed swimming calmly in places once thought impossible for vertebrates. Not many, and not in large numbers, but enough to prove that the boundary of life lies deeper than we once believed. And still, for every observation made, there are vast regions untouched. The Hadal zone is not one continuous plain. It is fragmented, made up of isolated trenches scattered across the ocean floor. Each trench is separated by thousands of kilometers of shallower seafloor. This means populations are cut off from one another, evolving in isolation for millions of years. Conditions vary subtly from trench to trench. Temperature differences, chemical composition, seismic activity. Over time, these differences shape life in ways we're only beginning to glimpse. When we send a robotic lander down into one of these trenches, it descends slowly, sometimes taking hours to reach the bottom. Its lights pierce a darkness that has not seen illumination for centuries, maybe longer. The beam reveals sediment, occasional movement, the quiet presence of a world that does not react to human attention. There is no fleeing, no curiosity, just continuation. What we see in those moments is not a complete picture. It is a narrow slice, a small cone of visibility in an environment that stretches outward and downward beyond the reach of the light. Cameras record what happens to cross their view, but most of the Hadal zone remains unobserved, unrecorded, and unvisited. This is not because of lack of interest. It is because of difficulty. Every descent is expensive. Every machine sent down risks failure. Pressure crushes seals. Cold embrittles materials. Communication delays complicate control. Retrieval is never guaranteed. A single malfunction can turn a multi-million-dollar mission into a silent object resting permanently on the ocean floor. So exploration proceeds slowly, carefully, with long gaps between missions, which means that most of what lives in the Hadal zone has never been seen by human eyes, not once. We infer its existence from traces, from chemical signatures, from unexpected readings, from patterns that suggest movement, consumption, interaction. The deep ocean leaves hints, not answers. As we continue downward in this exploration, we will encounter organisms that challenge our ideas of biology, environments that stretch engineering to its limits, and questions that remain unresolved not because they are unimportant, but because they are so hard to reach. The Hadal zone is not hiding its secrets out of hostility. It is simply very far away, very deep, and very patient. And as we move forward, staying with that depth, staying with that patience, we begin to see why this part of the ocean remains one of the last true frontiers on Earth. Not conquered, not charted, but quietly existing beneath everything we think we know. When people imagine unexplored places on Earth, their minds often drift upward. Snow-covered peaks, dense jungles, distant deserts, maybe even the far side of the moon. Very rarely do we imagine what lies directly beneath us, beneath the shipping lanes, beneath the storms and the calm seas, beneath the familiar blues of maps and screens. And yet, the deepest and least accessible frontier on this planet is not above our heads. It is below our feet, hidden under kilometers of water, beginning where the ocean floor simply drops away. The Hadal zone is the deepest region of the ocean, and calling it a zone almost feels too neat for something so vast, fragmented, and extreme. It begins at depths where the seafloor no longer slopes gently, but plunges into narrow, elongated trenches carved by tectonic forces over millions of years. These trenches form where massive plates of Earth's crust collide, and one is forced beneath another, dragging the ocean floor down into darkness. What results are long, steep valleys, some stretching for thousands of kilometers, all of them deeper than anything humans can comfortably comprehend. Unlike shallower ocean regions, the Hadal zone is not a continuous layer wrapping around the globe. It exists in pieces, scattered like deep scars across the ocean basins. Each trench is isolated, separated from the others by vast expanses of shallower seafloor. This isolation matters. It means that the Hadal zone is not one environment but many, each with its own conditions, its own history and its own forms of life, shaped slowly and independently over geological time. The name itself comes from Hades, the ancient Greek underworld, a fitting reference not because these depths are hostile in a dramatic sense, but because they are profoundly removed from the world we know. Light does not reach here. Sound behaves differently. Time feels altered, not because it actually slows, but because nothing moves quickly. Sediment settles at a pace so slow that a single centimetre may represent centuries of accumulation. Change happens, but quietly. At around 6,000 metres below the surface, sunlight has long since vanished. Even the faint blue glow that penetrates the upper deep sea is gone. What remains is complete darkness, not interrupted by day or night, seasons, or weather. The Hadal zone does not know the sun. It does not respond to storms or surface temperatures. Its environment is shaped by gravity, pressure, chemistry, and the slow fall of organic matter from far above. Pressure is the defining feature of this realm. For every 10 meters you descend into the ocean, pressure increases by roughly 1 atmosphere. At the surface, your body is accustomed to 1. In the Hadal zone, pressure can exceed 1,000 atmospheres. This is not pressure you feel gradually building. It is a constant, overwhelming force applied evenly in all directions. It presses on every surface, every joint, every material flaw. At these depths, steel can buckle if improperly designed. Glass shatters. Air-filled spaces collapse instantly. This is why submarines capable of reaching the Hadal zone are rare, and why most exploration relies on unmanned vehicles. Even then, failure is always a possibility. A single compromised seal can mean implosion. ending a mission in milliseconds. Temperature adds another layer of extremity. The water in the Hadal zone hovers just above freezing, typically between 1 and 4 degrees Celsius. There is no warmth from sunlight, no seasonal variation. This cold is stable and persistent. Combined with pressure, it creates an environment that challenges the basic chemistry of life as we understand it. And yet, despite all of this, the Hadal zone is not empty. For a long time, scientists assumed it would be. Early deep-sea expeditions, limited by technology and expectation, suggested that life became scarce beyond certain depths. The idea seemed logical. No light means no photosynthesis. No plants means no food. No food means no life. But the ocean does not operate on simple assumptions. Organic material from the surface slowly sinks through the water column. Dead plankton, waste, fragments of once-living organisms drift downward in a constant thin rain. Most of it is consumed by creatures higher up, recycled long before it reaches the trenches. What does arrive at the bottom is sparse and irregular, but over time, it adds up. In the Hadal zone, this material accumulates in trench floors, forming sediment rich in organic carbon. This sediment becomes the foundation of deep ecosystems. Microorganisms thrive within it, breaking down organic matter, releasing nutrients, supporting larger organisms. In some trenches, chemical reactions between seawater and exposed rock provide additional energy sources. Life here is not fast or abundant, but it is persistent. The first confirmed evidence of life at extreme trench depths came as a surprise. Early sampling missions recovered living organisms from depths previously thought uninhabitable. Amphipods, translucent crustaceans resembling oversized shrimp, were found thriving in trenches more than 10 kilometers deep. Their bodies were soft, flexible, adapted to withstand crushing pressure. Their metabolism was slow, efficient, suited to scarcity. Even more surprising was the discovery of fish at these depths. For years it was believed that vertebrates could not survive beyond a certain pressure threshold. Their cellular structures, it was thought, would fail, but footage and specimens proved otherwise. Certain species of snailfish were observed swimming calmly along trench floors, their gelatinous bodies and specialized proteins allowing them to function where no fish was expected to exist. These discoveries forced scientists to revise assumptions about the limits of life. They also raised new questions. How did these organisms evolve? How long have they been there? And how many more remain unseen? Exploration of the Hadal zone is limited not just by technology, but by sheer scale. Trenches are vast. A single expedition might survey only a few square kilometers, a tiny fraction of a trench that stretches hundreds or thousands of kilometers in length. Cameras capture what passes in front of them, but much of the environment remains beyond view. The most famous trench, the Mariana Trench, has become almost symbolic of oceanic depth. Its deepest known point, Challenger Deep, lies nearly 11 kilometers beneath the surface. Despite its notoriety, only a handful of missions have reached it. Each visit has been brief. Each has revealed only fragments of a much larger picture. Other trenches are even less explored. The Tonga Trench, the Kuril-Kamchatka Trench, the Philippine Trench. Names that appear on maps but remain largely theoretical in terms of lived observation. We know their depths, we know their locations, but we do not know their daily rhythms, their biological communities, their full complexity. Communication poses another challenge. Radio waves do not travel well through water, especially at depth. Submersibles rely on cables, acoustic signals, or delayed data retrieval. Real-time control is difficult. Missions must be carefully planned in advance, with limited ability to respond to unexpected discoveries. This limitation shapes what we see. We tend to observe what we expect to find. Cameras are placed near the seafloor, baited to attract scavengers. They capture organisms drawn to food, not necessarily those that live differently. Creatures that avoid bait, that burrow, that move slowly or infrequently, may never appear on camera at all. As a result, the Hadal zone remains, in many ways, defined by absence. Absence of light. Absence of sound as we know it. Absence of comprehensive data. It is a frontier not because it is dramatic, but because it is inaccessible. There is also a psychological barrier. Humans are surface dwellers. Our instincts are tuned to horizons, skies, and breathable air. Depth triggers discomfort. The idea of being trapped beneath kilometres of water, surrounded by pressure, unable to escape quickly, runs counter to our sense of control. Even remotely, the deep ocean feels unsettling, and yet that discomfort is part of what makes the Hadal zone so compelling. It represents a reminder that Earth is not fully known, that even now in an age of satellites and global networks, there are places that remain largely untouched, not because they are hidden, but because they are hard to reach. The Hadal zone does not announce itself. It does not produce towering features visible from space. It exists quietly, doing what it has always done, shaped by tectonics, chemistry, and time. Its creatures live without awareness of the surface world. They do not know ships pass overhead. They do not know humans debate their existence. As exploration continues slowly and cautiously, each new descent adds a little more detail to our understanding. A new species observed, a new behaviour recorded, a new reminder that life adapts in ways we do not always anticipate. And as we remain here, at this depth, considering what it means for a place to be both part of Earth and almost entirely beyond human reach, the next question begins to form naturally. Not about what lives there, but about why humans themselves cannot follow, and where the limits of our bodies truly lie as the ocean continues downward. There is a quiet assumption many people carry without realising it, that with enough training, enough equipment, and enough courage, a human can eventually go anywhere. We can climb the highest mountains, endure extreme cold, survive in space, and descend beneath the ocean surface. Depth, like height, feels like a challenge waiting to be solved. But the ocean is not simply a reversed mountain. It is an environment governed by rules that do not bend easily, and at a certain point they stop bending at all. To understand how deep is too deep for the human body, it helps to begin not with the Hadal zone itself, but with the body you are in right now. A body built for life at the surface, adapted over millions of years to breathe air, regulate temperature within a narrow range, and exist under a very specific amount of pressure. That pressure, the weight of the atmosphere pressing down on you, is something you almost never notice. It is constant, gentle, and familiar. Your body has evolved to expect it. The moment you leave that pressure behind, things begin to change. Even shallow dives introduce the body to an environment it was not designed for. At just a few meters underwater, pressure increases noticeably. Ears need to be equalized. Sinuses respond. The chest feels different. These are mild signals, easily managed, but they are the first hints that the ocean does not negotiate. Pressure increases predictably and relentlessly with depth, regardless of experience or intention. At 10 meters below the surface, pressure has doubled. At 30 meters, it has quadrupled. This is the depth range where recreational scuba divers typically operate, and even here, strict limits apply. Breathing compressed air introduces nitrogen into the bloodstream, and too much nitrogen, absorbed too quickly or released too fast, can cause decompression sickness. The bends, bubbles forming in tissues and blood vessels, pain, paralysis, even death if not treated promptly. This is not a failure of skill. It is chemistry and physics acting on a body that cannot change its structure on demand. As divers descend further, other problems appear. Nitrogen narcosis, sometimes called the rapture of the deep, affects cognition, reaction time, and judgment. Simple decisions become difficult. Euphoria or anxiety can take hold. At depths beyond 50 meters, oxygen itself becomes toxic. Oxygen toxicity can trigger seizures without warning, a deadly risk underwater. These limits are why deep diving requires specialised gas mixtures, replacing nitrogen with helium to reduce narcosis, carefully controlling oxygen levels to avoid toxicity. Even with these adjustments, the margin for error remains thin. Human diving records, achieved by elite individuals with years of training and support teams, push beyond 100 metres, sometimes a little more. But these feats are rare, dangerous, and temporary. Beyond that range, the human body simply cannot function in open water. The reasons are not mysterious. They are structural. The body contains air-filled spaces, lungs, sinuses, middle ears. As pressure increases, these spaces compress. At extreme depths, without rigid protection, they collapse entirely. The lungs are especially vulnerable. Compressed air at depth increases the partial pressure of gases, altering how they dissolve into tissues. Even if a diver could somehow avoid narcosis and oxygen toxicity, the mechanics of breathing become impossible. The chest wall cannot expand against the surrounding pressure. Muscles are not strong enough. The body cannot draw breath. Blood itself behaves differently under extreme pressure. Gases dissolve more readily. Cellular processes are disrupted. Proteins can change shape. Enzymes may stop functioning correctly. The chemistry of life begins to drift away from the narrow range that human biology depends on. Cold compounds these problems. Deep ocean temperatures hover near freezing. Hypothermia sets in rapidly without protection. Heat loss increases under pressure. Circulation shifts. Muscles stiffen. Reaction time slows. And then there is time. Even if a human could survive momentarily at great depth, returning safely to the surface introduces another set of constraints. Decompression must be slow and controlled. Too fast and dissolved gases form bubbles in tissues. Too slow and exposure risks increase. Deep dives require hours or days of staged decompression, sometimes inside pressurized chambers, carefully monitored. All of this applies within the upper reaches of the deep ocean. Now consider what happens when depth increases by orders of magnitude. The Hadal zone begins at around 6,000 meters. At this depth, pressure exceeds 600 atmospheres. That is 600 times the pressure your body experiences right now. No human suit can withstand that pressure while remaining flexible enough for movement. No breathing system can operate under those conditions. No tissue in the human body is adapted to function chemically at that pressure. At 10,000 meters, pressure approaches 1,000 atmospheres. This is not an environment where the human body can be slowly trained to adapt. There is no acclimatization curve, no incremental adjustment. The difference is categorical, not gradual. This is why human presence in the Hadal zone depends entirely on submersibles, rigid shells, often spherical, designed to distribute pressure evenly, thick walls made of steel, titanium or advanced composites, no windows or very small ones, life support systems that maintain internal pressure at surface levels, creating a tiny pocket of Earth's atmosphere surrounded by crushing force. Inside these vessels, humans are not experiencing the Hadal zone directly. They are insulated from it, separated by engineering. The environment outside would destroy the body instantly if exposed. Implosion would occur faster than nerves could transmit pain. There would be no sensation, no warning, just physics resolving itself. This distinction matters. When we say humans have reached the deepest parts of the ocean, what we really mean is that machines carrying humans have briefly touched those depths. The body itself has never been there unprotected. It cannot be. Even with submersibles, the risks are significant. Pressure does not forgive material flaws. A microscopic crack can become a failure point. Repeated stress weakens structures. The deeper the dive, the less room there is for error. This is why so few human descents into the Hadal zone have occurred. Each mission is expensive, complex, and inherently dangerous. There is no rescue capability at those depths, no backup vessel waiting nearby. If something goes wrong, there is no intervention. The margin between success and disaster is measured in millimeters of material integrity. The contrast between this fragility and the presence of life outside the submersible is striking. Creatures living in the Hadal zone do not resist pressure, they accept it. Their bodies contain little or no gas-filled space. They are composed mostly of water, which is incompressible. Their tissues are soft, flexible. Their cellular membranes are adapted to function under constant compression. Proteins are stabilized by compounds that prevent them from deforming. Enzymes are tuned to work under conditions that would disable surface organisms. From the perspective of physics, these organisms are not fighting their environment. They are aligned with it. Humans, by contrast, carry an environment within them that must be defended. Air, warmth, pressure balance. The deeper we go, the harder that defense becomes. At some point, it becomes impossible. This raises an uncomfortable realization. There are places on Earth where humans do not belong, not temporarily, but fundamentally. Places where our biology cannot function, no matter how advanced our technology becomes, unless we completely isolate ourselves from the surrounding environment. Space is often described this way, but the deep ocean shares many of the same constraints: vacuum versus pressure, temperature extremes, radiation versus chemical stress. In both cases, survival depends on creating an artificial bubble that mimics the conditions our bodies expect. The difference is that space feels distant and abstract, while the ocean is right here, beneath ships, beneath coastlines, beneath daily life. When considering the limits of the human body, it becomes clear that depth is not just a number. It is a boundary defined by biology, by the structure of lungs, blood, cells, and chemistry. Beyond a certain point, depth does not invite adaptation. It enforces exclusion. This does not mean exploration stops. It changes form. Robotic vehicles replace divers. Sensors replace eyes. Samples are collected mechanically. Data is interpreted remotely. Humans extend their reach through machines, not by transforming their bodies, but by acknowledging their limits. There is a humility in this approach, an acceptance that intelligence does not require dominance, that understanding does not require presence. The Hadal zone can be studied without being occupied, and as exploration continues, this separation between observer and environment becomes part of the story. We are learning about a world that exists independently of us, governed by rules that do not adjust for human comfort. As we move forward from this point, the focus shifts naturally. If humans cannot survive these depths, and yet life thrives there, then the question is no longer about our limits, but about theirs, about what kinds of bodies can endure such pressure, and what forms evolution takes when survival depends not on resisting the environment, but on becoming compatible with it. That is where attention turns next, toward the immense force pressing down on the Hadal zone, and the strange ways life responds to it. Pressure is one of those forces that rarely enters everyday thought. It is always present, always pressing down, yet so evenly distributed that it disappears into the background of experience. You do not feel the atmosphere resting on your shoulders. You do not notice the weight of the air filling the room around you. It becomes noticeable only when it changes, when ears pop during a flight, when a sealed container resists opening, when weather shifts bring that dull, familiar headache. But these are small variations, tiny ripples in a force that is otherwise constant. In the Hadal zone, pressure is no longer subtle. It is not a background condition. It is the dominant reality. To understand just how extreme this pressure is, it helps to strip away intuition, because intuition fails almost immediately. At sea level, the atmosphere presses down with about 101 kilopascals of force, roughly the weight of a car distributed across the surface of your body. That sounds dramatic, but because the pressure is equal inside and outside your body, you feel nothing. Your tissues, fluids, and air-filled spaces are in balance. As you descend into the ocean, that balance begins to shift. water is far denser than air. Every 10 meters of depth adds another full atmosphere of pressure. 10 meters is about the height of a 3-story building. It is a distance you could walk down a staircase in less than a minute. And yet, underwater, each of those 10-meter steps stacks another invisible weight on everything below. At 100 meters, the pressure is already 11 times greater than at the surface. At 1,000 meters, it is over 100 times greater. By the time you reach 6,000 meters, the threshold of the Hadal zone, pressure exceeds 600 atmospheres. At the deepest points, it climbs past 1,000. Numbers like this are difficult to picture, so comparisons are often used. Imagine a fully loaded commercial jet resting on a single postage stamp. Imagine a mountain pressing down on every square centimetre of your body. Imagine thousands of tons of force squeezing inward from all directions at once. Even these images fall short because pressure at depth is not directional. It does not come from above, it surrounds. This is what makes it so destructive. If pressure only pushed downward, structures could be reinforced underneath. But pressure underwater presses equally from all sides. Any weakness, any asymmetry, any trapped pocket of air becomes a failure point. The force does not need speed. It does not need motion. It is constant, patient, and absolute. This is why implosions in deep-sea environments are so violent. When a structure fails, even slightly, the surrounding pressure rushes inward at tremendous speed. The collapse happens faster than sound can travel through the material. There is no gradual deformation. One moment, the structure exists. The next, it does not. For biological organisms, the challenge is just as severe, but the solutions are very different. Life in the Hadal zone does not build rigid shells to resist pressure. That approach would require materials far stronger than biology can produce. Instead, deep-sea organisms remove the problem altogether. They eliminate air. They minimize empty space. Their bodies are mostly water, which cannot be compressed under these conditions. Their tissues flex rather than resist. Pressure passes through them rather than acting against them. At the cellular level, pressure still poses a problem. Proteins, the molecular machines that carry out nearly all biological processes, have specific shapes. Those shapes determine how they function. Under extreme pressure, proteins can unfold, losing their structure and becoming useless. For surface organisms, this happens at pressures far below those found in the Hadal zone. Hadal organisms solve this chemically. They produce compounds known as piezolites, small molecules that stabilize proteins under pressure. These molecules prevent proteins from collapsing or changing shape, allowing essential reactions to continue. It is a subtle adjustment, but without it, life at these depths would not be possible. Cell membranes face similar challenges. Membranes must remain flexible enough to allow transport of nutrients and waste, but stable enough to hold cells together. Under pressure, membranes can become rigid or leaky. Deep-sea organisms modify the composition of their membranes, increasing certain lipids that maintain fluidity even when squeezed by immense force. These adaptations are not optional. Without them, pressure would silently dismantle the machinery of life. What is striking is how complete this adaptation is. Hadal organisms are not temporarily tolerating pressure. They are not surviving at the edge of their limits. They are optimized for it. In laboratory experiments, when some of these organisms are brought to the surface, they do not recover. The sudden loss of pressure is as damaging to them as extreme pressure would be to us. Their proteins destabilize, their membranes fail, their internal balance collapses. For them, the surface is hostile. This inversion of habitability challenges a deeply human assumption. We tend to think of the surface as normal and extremes as deviations. But from the perspective of a Hadal organism, the surface is an extreme environment. Low pressure, high temperature variability, intense radiation from sunlight, conditions that would be intolerable. Pressure also affects time and movement in subtle ways. In the Hadal zone, water density increases slightly under pressure, altering how particles sink and how currents behave. Movement is slower, more deliberate. There is no turbulence like that found near the surface, no waves, no storms. The water is heavy, still and stable. Sound travels differently as well. Low-frequency sounds can propagate over long distances, bending along pressure gradients. This means that seismic activity, landslides, or distant geological events can be detected across vast stretches of the deep ocean. The Hadal zone is not silent in an absolute sense, but it is quiet in a way that is difficult to describe. Sounds arrive softened, stretched, stripped of sharp edges. For human-made machines, pressure dictates every design choice. Submersibles capable of reaching extreme depths use spherical pressure vessels because spheres distribute stress evenly. Flat surfaces are avoided. Corners are dangerous. Windows, if present at all, are small and thick, often made of specialized acrylics designed to deform predictably rather than shatter. Even with these precautions, depth ratings are conservative. Engineers design for pressures beyond what they expect to encounter, knowing that materials fatigue, that microfractures grow, that repeated dives weaken structures over time. A submersible that survives one deep dive is not guaranteed to survive the next. Pressure also limits observation time. The longer a vehicle remains at depth, the more stress accumulates. Seals creep, materials compress. Electrical systems are exposed to conditions they were never meant to endure for long periods. This is why many deep-sea missions are brief, sometimes only hours on the seafloor before ascent begins. As a result, our glimpses of the Hadal zone are fleeting, short windows of light in an otherwise permanent darkness. A lander touches down, collects data and leaves. What happens there the rest of the time remains unknown. Pressure shapes not only bodies and machines but landscapes. Trench floors are not static. Sediments shift under their own weight. Slopes fail. Submarine landslides occur, moving enormous volumes of material. These events can reshape habitats in moments, burying some areas and exposing others. Life must be resilient not only to pressure, but to sudden environmental change. Earthquakes play a role as well. Many trenches lie along active subduction zones. Seismic activity can send shock waves through the deep ocean, triggering sediment flows and altering chemical gradients. Hadal organisms experience these events without warning, without shelter. Survival depends on flexibility, both physical and ecological. Pressure, in this context, is not merely an obstacle. It is an organizing force. It defines which molecules function, which structures hold together, which forms of life can exist. It filters possibilities. For humans, pressure beyond a certain point represents an absolute boundary. For life in the Hadal zone, it represents home. This difference is essential to understanding why so much of the deep ocean remains beyond our reach. It is not just that we lack technology, it is that our biology places us on the outside. We are visitors peering in through thick walls protected by engineering, unable to step out and belong. As attention continues to sink deeper into this environment, pressure remains the constant companion. It is present in every observation, every limitation, every adaptation. It explains why the Hadal zone is not simply deeper water, but a fundamentally different world. And once pressure is acknowledged as the dominant force shaping this realm, another realization follows naturally. In a place defined by crushing force and perpetual darkness, sunlight is not just absent, it is irrelevant. Which leads directly into the next condition that defines life here, a condition just as absolute as pressure, and perhaps even more alien to surface experience. Sunlight is so deeply woven into human life that its absence is difficult to imagine as anything other than temporary. Night falls, but morning comes. Clouds gather, but eventually break. Even underground spaces are usually entered with the expectation of returning to the surface. Light for us is a given. It sets our schedules, regulates our sleep, warms our planet, and powers nearly every ecosystem we know. Remove it, and the familiar world begins to unravel very quickly. In the Hadal zone, sunlight is not delayed, filtered, or weakened. it is completely gone. Not dim, not distant. Gone. Long before reaching these depths, the last usable photons from the sun have already been absorbed by the water above. Even the faint blue wavelengths that penetrate deepest vanish thousands of meters higher. By the time the Hadal zone begins, the concept of day and night no longer applies. There is no dawn, no dusk, no shadow, no glow on the horizon. The darkness is uninterrupted and permanent. This absence shapes everything. On the surface, sunlight is more than illumination. It is energy. Photosynthesis uses it to convert carbon dioxide and water into sugars, forming the base of most food webs. Plants grow. Herbivores eat plants. Predators eat herbivores. Even ecosystems that seem disconnected from plants rely on this energy indirectly. Sunlight is the engine that keeps the biosphere running. In a world without sunlight, that engine does not exist. The Hadal zone receives no energy from above in the form of light. No photosynthesis occurs there. No plants grow, no algae bloom. If life exists, and it does, it must find another way to power itself. The most obvious alternative is detritus. Organic material produced at the surface eventually dies, breaks apart and sinks. Tiny fragments of plankton, fecal pellets, bits of dead organisms all drift downward through the water column. This slow, constant fall is sometimes called marine snow, though it looks nothing like snow in any familiar sense. It is sparse, uneven, and unpredictable. By the time this material reaches Hadal depths, most of it has already been consumed. What remains is low in energy and arrives irregularly. Entire days or weeks may pass with little new input. Life here cannot rely on abundance, it must rely on patience. Many Hadal organisms are scavengers, adapted to exploit whatever arrives. Their metabolisms are slow, their movements are deliberate, they conserve energy wherever possible. When food appears, they take advantage, but they do not expect it to be frequent. Others rely on something even more unfamiliar. In certain deep-sea environments, chemical reactions provide energy independent of sunlight. These are known as chemosynthetic ecosystems. Instead of using light to build organic molecules, bacteria use chemical gradients. Hydrogen sulfide, methane, ammonia, and other compounds released from the seafloor can be oxidized to produce energy. This energy is then used to fix carbon, forming the base of a food web. Hydrothermal vents are the most famous example of this process, though most vents occur at shallower depth than the Hadal zone. Still, similar chemical processes can occur in trenches where tectonic activity exposes minerals and releases reactive compounds. Microbial communities form around these energy sources, supporting larger organisms. In these ecosystems, the sun is irrelevant. Life is powered by the planet itself. The absence of sunlight also removes visual cues that dominate surface life. There are no colours as we know them. Colour exists only as a property of reflected light. Without light, there is nothing to reflect. Many Hadal organisms lack pigmentation altogether. Others retain coloration, but it serves purposes unrelated to camouflage or display, such as structural integrity or chemical protection. Vision too becomes optional. Some deep-sea creatures have eyes, but many do not. In total darkness, eyes offer little advantage unless paired with a source of light. Maintaining complex visual systems is energetically expensive. If they provide no benefit, evolution tends to discard them. Instead, other senses become dominant. Touch, vibration detection, chemical sensing. Water carries information in ways air does not. Subtle changes in pressure reveal movement. Dissolved chemicals signal the presence of food, predators, or mates. In the Hadal zone, awareness is not visual, it is distributed through the body. For organisms that do use light, that light comes from within. Bioluminescence is common throughout the deep ocean, though it becomes less frequent in the deepest trenches. Producing light requires energy, and in an environment where energy is scarce, efficiency matters. Still, Some Hadal organisms retain the ability to emit light, often for specific purposes. Light can be used to attract prey, confuse predators, or communicate with others of the same species. It may appear as brief flashes, steady glows, or patterns along the body. Unlike surface light, bioluminescence is controlled. It is turned on and off as needed. It does not illuminate the environment so much as punctuate it. Imagine darkness so complete that even a faint spark becomes overwhelming. In such a setting, light is not background, it is signal. The physics of light behave differently underwater as well. Water absorbs light rapidly. Even bioluminescent signals do not travel far, a few meters, perhaps less. This limits communication range. Signals are intimate, local. Encounters happen up close. This has consequences for behavior. Many deep-sea organisms are solitary or sparsely distributed. Large gatherings are rare. Mating encounters may depend on chemical trails rather than visual displays. Predation often involves ambush rather than pursuit. The absence of sunlight also means the absence of daily cycles. On the surface, life is synchronized to the rising and setting of the sun. Circadian rhythms govern sleep, feeding, migration. In the Hadal zone, there is no external clock. Time is not marked by light. Some organisms still maintain internal rhythms, perhaps inherited from shallower ancestors. Others may operate entirely in response to environmental cues like food availability or pressure changes caused by tides. These cues are subtle, slow, and often indirect. Without sunlight, temperature remains stable. There are no warm afternoons or cool nights. The water stays cold, nearly constant. This stability simplifies some aspects of survival, while complicating others. Chemical reactions proceed at predictable rates, but growth is slow. Development takes time. In such an environment, speed is rarely advantageous. Rapid movement wastes energy. Fast reproduction requires resources that may not arrive. Longevity becomes a viable strategy. Some deep-sea organisms may live far longer than their surface counterparts, growing slowly, reproducing infrequently, but persisting. The absence of sunlight also affects how we study these environments. Human exploration relies heavily on light. Cameras need illumination. Observations depend on visibility. In the Hadal zone, every expedition introduces artificial light into an environment that has never experienced it. Bright lamps attached to submersibles cut through darkness, revealing sediment, creatures, movement. But this light is intrusive. Some organisms flee, others freeze, some are attracted. Behavior observed under artificial light may not reflect normal activity. We are always aware in these moments that what we see is filtered not only by limited coverage, but by the act of observation itself. There is also the question of scale. Without sunlight, there are no visual landmarks, no distant reference points. Everything exists in close proximity. Space feels compressed, even though the trenches are vast. A camera frame shows only what is directly in front of it. Beyond that, darkness resumes. This makes mapping difficult. Sonar helps, but sonar produces abstractions, shapes, gradients. It does not convey texture or behavior. The Hadal zone resists being fully rendered. For humans, the idea of a world without sunlight carries psychological weight. Darkness is often associated with danger, with absence, with fear. But in the Hadal zone, darkness is not hostile, it is simply normal. Life there does not fear the dark, it evolved within it. This perspective matters. When we describe these environments as extreme or alien, we are describing them from a surface-based viewpoint. For the organisms living there, the surface world would be extreme, blinding light, rapid temperature changes, ultraviolet radiation, noise, turbulence. In that sense, the Hadal zone is not deprived, it is specialized. The absence of sunlight strips life down to essentials. Energy must be conserved. Signals must be efficient. Structures must be stable. There is little room for excess. This does not mean life is simple. it means it is precise. As we continue deeper into understanding this environment, it becomes clear that darkness is not just a lack of light. It is a condition that reshapes biology, behaviour, and ecosystems from the ground up. It defines what kinds of organisms can exist, how they interact, and how they persist over time. And once light is removed from the equation, another realization follows naturally. In a world without sunlight, without visual horizons, without daily cycles, silence takes on a different meaning. Not silence as the absence of sound, but silence as the absence of constant disturbance. A stillness shaped by depth, pressure, and time itself. That stillness waits just beyond the edge of what we can hear. Deeper still, where movement slows and the ocean settles into something quieter than anything at the surface. Silence is usually defined by contrast. A quiet room after a loud gathering, a pause between words, the moment when machinery shuts down and the background hum disappears. On the surface of the world, silence is temporary and fragile. It is broken by wind, insects, distant engines, the constant motion of air and life. Even at night, sound leaks in from somewhere. There is always something moving. Below 8 kilometers of water, silence takes on a different character. It is not the absence of sound in an absolute sense. Sound still exists in the Hadal zone. The ocean is never completely mute, but the kind of sound that dominates life at the surface, the unpredictable, overlapping noise of weather, animals and human activity, fades away as depth increases. What remains is something slower, deeper, and far more restrained. Sound behaves differently underwater. It travels faster than it does in air and over much longer distances. Low-frequency sounds, in particular, can move across entire ocean basins, bending along layers of temperature and pressure. At shallower depths, this creates a complex acoustic environment filled with echoes, interference, and constant motion. Waves crash, currents collide, marine life communicates, hunts, and navigates using sound. As you descend deeper, many of these sources disappear. Surface noise weakens with depth. Waves no longer reach. Wind-driven turbulence fades. Human sounds, ships, engines, propellers, diminish until they are little more than distant murmurs, if they can be detected at all. Even biological noise decreases. Large animals are rare. Vocalizations are infrequent. Movement is slow. By the time you reach depths beyond 8 kilometers, the acoustic environment has thinned dramatically. What remains are sounds tied to the planet itself. The slow groan of tectonic plates shifting, the distant rumble of undersea earthquakes, the occasional collapse of sediment along trench walls. These sounds are not sharp or sudden. They arrive softened, stretched out, filtered by kilometers of water and pressure. They feel less like events and more like background conditions. Between these rare disturbances, there are long intervals of near stillness. This stillness is not empty. It is dense. It presses in, much like the water itself. In the Hadal zone, silence is not a gap between sounds. It is the default state. For organisms living here, this has profound implications. Sound, like light, is a source of information. In the absence of constant noise, even subtle vibrations become meaningful. A small shift in water pressure, a faint movement of sediment, a chemical plume disturbed by passing motion. These signals stand out because there is little else competing with them. Deep-sea organisms are often exquisitely sensitive to vibration. Some have specialized sensory organs capable of detecting minute pressure changes. Others rely on distributed sensory cells along their bodies, allowing them to feel their surroundings rather than see or hear them in any familiar way. In a quiet environment, this sensitivity becomes an advantage. But the silence also reflects scarcity. Movement costs energy. Sound is often a byproduct of movement. In an environment where energy is limited, minimizing movement is beneficial. Many Hadal organisms move only when necessary. They rest for long periods. They drift. They wait. Predation, when it occurs, is often sudden and brief. A scavenger detects the presence of food through chemical cues. It moves toward it slowly. There is no chase, no pursuit across distances. The encounter is localized and efficient. Reproduction too adapts to silence. Without frequent encounters, many species rely on strategies that do not require active searching. Some release gametes into the water column, trusting currents to bring them together. Others may reproduce infrequently, with long lifespans compensating for low reproductive rates. The quiet also affects how ecosystems respond to change. On the surface, disturbances are frequent. Storms, tides, temperature swings. Life is adapted to constant variation. In the Hadal zone, change is rare but consequential. When it happens, it leaves lasting marks. A submarine landslide can bury habitats under meters of sediment. An earthquake can alter chemical flows, reshaping microbial communities. These events may occur years or decades apart. In between, conditions remain stable. This stability creates a different relationship with time. Biological processes unfold slowly. Growth rates are low. Recovery from disturbance takes longer. Evolution proceeds under consistent pressure, both literal and figurative. For human explorers, this silence can feel unsettling. Submersibles descending into these depths carry their own noise. Motors hum, thrusters engage, instruments click. Inside the pressure sphere, human occupants hear the sounds of life support systems, pumps circulating air, the quiet creaks of the hull adjusting to pressure. These sounds become prominent because there is nothing else to compete with them. Outside, the ocean absorbs much of this noise. The submersible becomes a moving island of sound in a vast quiet sea. Cameras reveal sediment drifting lazily. Occasional organisms appear and vanish into darkness. The sense of isolation is profound. There is also the awareness that communication with the surface is limited. Acoustic signals take time to travel. Responses are delayed. The crew exists temporarily in a separate acoustic world, buffered from the noise of human activity above. This separation highlights a deeper truth. The Hadal zone exists largely outside the sensory reach of humans, not just visually, but acoustically. We cannot hear it without specialized instruments. We cannot perceive its rhythms without translation. Hydrophones placed in deep water have revealed patterns we would otherwise never know. The faint songs of distant whales passing overhead, the steady crackle of microseismic activity, the occasional sharp sound of ice carving in polar regions, transmitted across entire ocean basins. These sounds arrive altered but present. Yet below 8 kilometers, even these signals grow faint. The trench walls act as barriers, reflecting and absorbing sound. The geometry of the environment creates pockets of acoustic isolation. In these pockets, local sounds dominate and distant ones fade. For organisms living there, this isolation may contribute to speciation. Limited communication and movement between trench systems reduce gene flow. Over time, populations diverge. Unique forms evolve, adapted not only to pressure and darkness, but to acoustic solitude. The silence also influences behavior in ways that are difficult to observe. Without frequent sound cues, organisms may rely more heavily on chemical communication. Pheromones, dissolved substances, subtle gradients in the water become primary signals. These signals persist longer than sound, spreading slowly, lingering. This creates an environment where information travels at a different pace. Nothing is immediate, nothing is urgent. Responses unfold over hours, days, sometimes longer. From a human perspective, this can feel almost unreal. We're accustomed to constant stimulation. Noise fills our environments, even when we seek quiet. Complete stillness is rare and often uncomfortable. In the Hadal zone, stillness is normal. It is worth noting that this silence is not absolute. it can be broken. A falling object, whether natural or human-made, accelerates through the water column and eventually strikes the seafloor. The impact sends vibrations through sediment and water. Organisms detect it. Some investigate, others retreat. The environment responds briefly before returning to quiet. Similarly, the arrival of food can change the soundscape. A large carcass sinking from above creates turbulence as it descends. When it reaches the bottom, scavengers converge. Movement increases. The water becomes momentarily active. These events are rare, but significant. For researchers, these moments offer insight into community dynamics. They reveal who arrives first, who dominates, who waits, but they also underscore how unusual such activity is. Most of the time, nothing dramatic happens. This quiet persistence is part of why the Hadal zone remains difficult to understand. Short missions capture snapshots, not continuous narratives. We see moments, not rhythms. We infer behaviour from brief observations, knowing that most of life unfolds beyond our view. The silence challenges storytelling. There are no constant events to describe, no obvious cycles. The drama, if it exists, is subtle and slow, and yet within this stillness life continues. Metabolisms hum quietly. Cells divide. Chemicals react. Organisms grow, reproduce, die. The absence of noise does not mean the absence of activity. It means activity occurs on scales and tempos that do not announce themselves. As attention lingers here, in this quiet depth, another aspect of the Hadal zone becomes more apparent. In an environment where movement is slow, light is absent, and sound is scarce, bodies themselves take on unfamiliar forms. Shapes that would seem fragile or impossible at the surface make sense here. Forms shaped not by speed or display, but by endurance. And it is those forms, adapted to this silent pressure, that begin to emerge as the next focus of attention. When we imagine creatures adapted to extreme environments, we often picture armour, spikes, thick hides, or aggressive forms built to fight their surroundings. That intuition comes from surface life, where survival frequently involves resisting predators, weather, or competition through strength and speed. In the Hadal zone, that logic quietly falls apart. Down here, nothing is built to fight the environment. Everything that survives has learned to yield to it. The creatures of the Hadal zone are not shaped by drama. They are shaped by pressure, darkness, scarcity, and time. Their bodies look unfamiliar not because they are monstrous, but because they are honest. Every structure reflects a compromise with forces that cannot be escaped. The most immediate difference is texture. Many Hadal organisms appear soft, almost fragile when seen on camera. Their bodies lack rigid skeletons or heavy shells. This softness is not a weakness. It is the only viable strategy. Hard structures resist pressure, and resistance creates stress. Stress creates failure. Soft tissues allow pressure to pass through without concentrating force in any one place. Water, which makes up most of their bodies, is effectively incompressible at these depths. By aligning their internal composition with their surroundings, these organisms eliminate the problem of crushing force rather than attempting to counter it. They do not brace themselves against the ocean, they become part of it. Take amphipods, for example, some of the most commonly observed animals in deep trenches. They resemble oversized shrimp, pale or translucent, with segmented bodies and delicate limbs. At first glance they look vulnerable, but amphipods dominate Hadal scavenging communities. They arrive quickly at foodfalls, sometimes in astonishing numbers, consuming organic matter with efficiency that suggests long familiarity with scarcity. Their success comes from flexibility and chemical resilience. Their exoskeletons are thinner than those of shallow water crustaceans. Their joints are adapted to move under pressure without seizing. Their internal chemistry includes compounds that protect proteins from deforming, allowing normal cellular processes to continue where surface organisms would fail almost instantly. Fish in the Hadal zone are even more counterintuitive. For years, it was assumed that vertebrates could not survive beyond a certain depth. Bones, it was thought, would not tolerate the pressure. But bone is not the issue. Air is. Hadal fish have reduced or absent swim bladders, the gas-filled organs that allow most fish to control buoyancy. Without gas-filled spaces, there is nothing to collapse. These fish often appear gelatinous, their muscles less dense than those of shallow water species. They are not built for speed. They do not chase prey over distances. Instead, they hover close to the seafloor, conserving energy, moving only when necessary. Their flesh, while soft, is perfectly adequate in an environment where there are few predators capable of rapid pursuit. The snailfish is a well-known example. Found at extraordinary depths, it looks almost unfinished by surface standards. Translucent skin, small eyes, a body that seems barely structured. But this form is precisely what allows it to exist where few others can. Its proteins are stabilized by pressure-adapted chemistry. Its membranes remain functional. Its cells operate normally under forces that would destroy surface fish at a fraction of the depth. Darkness shapes these bodies as much as pressure does. Without sunlight, vision becomes unreliable or irrelevant. Some Hadal organisms retain eyes, but these eyes are often small, simplified, or tuned to detect bioluminescence rather than reflected light. Others abandon eyes altogether. Maintaining visual systems requires energy. If that energy provides no return, it is better spent elsewhere. In place of vision, other sensory systems expand. Chemoreceptors detect dissolved substances in the water, allowing organisms to locate food or mates by scent rather than sight. Mechanoreceptors detect vibrations, pressure changes, and water movement. In a world where sound is scarce and light absent, touch and chemistry become the primary languages. Body shapes reflect this sensory shift. Long antennae, extended fins, filament-like appendages, these structures increase surface area, enhancing sensitivity to subtle environmental cues. They are not decorative, they are functional extensions of awareness. One striking feature of many Hadal organisms is their slow pace of life. Growth is gradual, reproduction is infrequent. Lifespans may be long, though measuring them is difficult. In an environment where food arrives unpredictably and energy is precious, rushing offers no advantage. Patience becomes a survival trait. This slow pace influences everything from metabolism to behavior. Muscles are adapted for endurance rather than power. Enzymes function efficiently at low temperatures. Cellular repair mechanisms may be prioritized over rapid growth. Damage accumulates slowly and recovery takes time. Predation in the Hadal zone reflects these constraints. There are predators, but encounters are rare. Chases are uncommon. Many predatory interactions rely on ambush or opportunism rather than pursuit. A scavenger may become prey if it moves carelessly. A predator may wait long periods for a single opportunity. Bioluminescence, when present, is used sparingly. Producing light costs energy. In an environment where energy budgets are tight, light is reserved for specific purposes. A brief flash to confuse a predator, a faint glow to lure prey, a signal to a potential mate at close range. Light is not a constant display, it is punctuation. Some Hadal organisms do not produce light at all. In total darkness, invisibility can be an advantage. Without light, there is no need for camouflage patterns or coloration. Many species are pale, transparent, or uniformly coloured. Pigmentation, like vision, is expendable. At the microscopic level, life in the Hadal zone becomes even more remarkable. Microorganisms thrive in sediments under immense pressure. Bacteria and archaea form complex communities, breaking down organic material, cycling nutrients, and supporting larger life forms. These microbes are often the true foundation of Hadal ecosystems, quietly processing energy in ways that remain poorly understood. Some are piezophiles, organisms that prefer high-pressure environments and grow poorly at surface pressure. Their enzymes and membranes are optimized for compression. When brought to the surface, they struggle or die. For them, pressure is not a stressor, it is a requirement. These microbial communities influence the chemistry of the seafloor. They affect how carbon is stored, how nutrients move, how sediments change over time. In this way, Hadal life plays a role in global processes despite being largely invisible. Isolation further shapes these creatures. Each trench is effectively an island, separated by vast distances of shallower seafloor that many Hadal organisms cannot cross. This isolation limits gene flow. Over millions of years, populations diverge, species become unique to specific trenches. Forms evolve that exist nowhere else on Earth. This means that much of Hadal biodiversity remains undiscovered. Every trench explored reveals species new to science, and most trenches have barely been sampled at all. The creatures we know are almost certainly a fraction of those that exist. This raises an important point. When we talk about the Hadal zone hiding creatures beyond human reach, we are not speaking metaphorically. These organisms are beyond our reach, not because they are hiding intentionally, but because the environment that sustains them excludes us. We cannot visit casually. We cannot stay long. We cannot interact directly. Our observations are brief, filtered through cameras and sensors. We see outlines, behaviours, fragments of existence. The rest continues without us. There is a temptation to imagine these creatures as ancient relics, unchanged for millions of years. In reality, evolution continues here as it does everywhere. Adaptations refine. Species respond to subtle environmental shifts. Change happens just slowly, quietly, without spectacle. Human influence has begun to reach even these depths. Microplastics have been found in trench sediments. Chemical signatures of pollution appear in unexpected places. The Hadal zone is not as isolated as it once was, but its inhabitants have not evolved to deal with rapid, human-driven change. Their resilience is tuned to geological timescales, not industrial ones. Understanding these creatures requires a shift in perspective. Survival here is not about dominance. It is about compatibility, not about speed or strength, but about chemical balance, structural flexibility and endurance. As attention lingers on these forms, shaped by darkness and pressure, another realization begins to emerge. If these creatures exist, adapted so precisely to conditions that seem impossible to us, then it follows that the boundaries of form and function are far wider than surface life suggests, and that leads naturally toward a deeper question. Not just what kinds of bodies survive here, but what shapes and structures evolution is capable of producing when freed from the assumptions of light, speed, and abundance. There is a quiet discomfort that arises when we encounter life forms that do not match our expectations. Not fear exactly, but a sense that something is out of place. Our minds are shaped by patterns. We learn, often unconsciously, what an animal is supposed to look like. Symmetry, familiar proportions, eyes where we expect them, limbs that suggest how something moves. When those cues are missing or rearranged, the brain hesitates. It searches for reference points and finds none. The Hadal zone is full of such hesitations. The forms that exist at these depths often appear wrong by surface standards. Too soft, too stretched, too transparent, too unfinished. They seem as though they should collapse, fail, or simply not function. And yet they do function, not briefly, not barely. They persist, reproduce, and thrive in conditions that exclude nearly all other complex life. What looks impossible to us is, in fact, optimized. One of the reasons these forms feel so strange is that we instinctively associate structure with strength. Thick bones, rigid shells, dense muscles. On land and in shallow water, these features provide leverage, protection, and speed. In the Hadal zone, they would be liabilities. Rigidity concentrates stress. Density increases energy demands. Elaborate structures cost resources that are not reliably available. So evolution lets go. Many Hadal organisms have bodies that seem to blur at the edges. Their outlines are soft, sometimes barely defined. They look almost fluid, as though they might dissolve into the water around them. This is not because they are fragile, it is because they are aligned with their environment at a fundamental level. Gelatinous tissues are common. These tissues are mostly water, held together by networks of proteins and connective material that flex under pressure. There is no resistance, no internal voids. Pressure passes through them evenly. Where a rigid organism would fracture, these bodies simply exist. Transparency often accompanies this softness. Without light, pigmentation offers little advantage. Producing pigments requires energy and raw materials. If those pigments do not serve a purpose, evolution removes them. The result is organisms you can see through, their internal organs faintly visible, suspended in bodies that seem more suggestion than substance. This transparency has another effect. It erases visual cues that predators might use. In darkness, where bioluminescence is the only light source, being transparent can make an organism nearly invisible. Light passes through rather than reflecting. Edges disappear. Some Hadal creatures take this a step further, reducing complexity wherever possible. Simplified nervous systems, reduced sensory organs, minimal musculature. Not because they are primitive, but because they are precise. Every structure attained serves a function that justifies its energy cost. There are also forms that seem exaggerated in one dimension while diminished in others. Long, thread-like appendages, extended antennae, narrow bodies with trailing filaments. These shapes increase surface area without adding mass. They enhance sensitivity to chemical gradients and subtle water movement. In an environment where food and mates are sparse, detecting faint signals is more important than moving quickly. Then, there are the mouths. Surface predators often have jaws built for speed and force, teeth arranged for tearing or crushing. In the Hadal zone, mouths are often large relative to body size, not because prey is abundant, but because opportunities are rare. When food appears, the ability to ingest a wide range of materials matters more than specialization. Scavengers, in particular, benefit from flexibility. A carcass arriving from above may be large, small, intact, or partially decomposed. Being able to consume whatever is available increases survival chances. This leads to mouths that seem oversized, expandable, or loosely structured. Some organisms possess stomachs capable of stretching dramatically, allowing them to store food for long periods. In an environment where meals may be separated by weeks or months, this is not excess, it is insurance. Eyes, when present, often look underdeveloped or oddly positioned. Some are reduced to light-sensitive patches rather than complex organs. Others are angled downward or forward in ways that seem inefficient by surface standards. But efficiency is relative. In darkness, eyes are not for forming images. They are for detecting light. Any light, even the faint glow of bioluminescence. In some cases, eyes are absent altogether. This absence can feel unsettling to human observers who rely so heavily on vision. But for these organisms, vision offers no advantage. Touch, chemistry, and vibration provide more reliable information. What makes these forms particularly unsettling is that they defy familiar categories. They are not clearly fish, not clearly invertebrates in the way we expect. They occupy spaces between definitions, transitional shapes that feel incomplete only because our categories are incomplete. This discomfort is amplified by scale. Some Hadal organisms are very small, barely visible without magnification. Others are surprisingly large, their size made possible by low metabolic rates and the absence of certain predators. When a large gelatinous form drifts into view on a camera feed, it can feel surreal. Not because it is threatening, but because it does not fit into the mental library of known animals. It is tempting to describe these creatures as alien. The word comes easily. But this framing misses something important. These organisms are not alien. They are Earth life, shaped by Earth conditions, following the same biochemical rules as all living things. What differs is the context. Evolution does not aim for familiarity. It aims for persistence. When conditions change, forms change. Remove sunlight and eyes lose importance. Increase pressure and rigidity becomes dangerous. Reduce food availability and speed loses value. Over time, the traits that remain are those that align with the environment, not with our expectations. This alignment produces bodies that look wrong, only because we are judging them by the wrong standards. There is also the matter of incomplete observation. Most footage from the Hadal zone comes from brief encounters. A camera descends, illuminates a small area, records what passes through the frame, and leaves. We see fragments of behaviour, isolated moments. We do not see full life cycles. We do not see development from juvenile to adult. We do not see how these organisms interact over long periods. Without that context, forms can seem even stranger. An organism observed briefly may look static or awkward simply because we have not seen how it moves when undisturbed. A posture captured on camera may not represent normal behaviour. Light itself may alter activity. There are also forms we have not seen at all. Sampling the Hadal zone is extremely limited. Nets are difficult to deploy accurately. Many organisms are fragile and do not survive retrieval. Others may live buried in sediment, emerging only occasionally. Some may avoid light entirely. The absence of evidence is not evidence of absence. Given how little we have observed, it is reasonable to assume that the known forms represent only a fraction of what exists. There may be body plans that challenge our definitions even further, structures that do not resemble anything currently described, life strategies that do not fit into existing categories. This is not speculation without basis. Each new trench explored has revealed species previously unknown. Each improvement in technology expands what we can detect, and each expansion reminds us how narrow our previous understanding was. The phrase "should not exist" reflects human expectation, not biological reality. It is a statement about our assumptions, not about nature's limits. Nature does not consult intuition. In the Hadal zone, evolution operates under constraints so different from those at the surface that entirely different solutions become viable. Forms that would fail instantly in shallow water persist effortlessly at depth. Bodies that look unstable are in fact precisely balanced. Structures that seem inefficient are perfectly tuned. There is a quiet lesson here. Familiarity is not a measure of validity. Appearance does not indicate capability. Life does not need to look strong to be resilient. As attention stays with these strange forms, adapted to darkness and pressure in ways that defy surface logic, another realization begins to surface. These bodies are not just strange in shape, they are strange in substance. Their chemistry, their internal processes, their very building blocks operate under rules that differ subtly but significantly from those we know. And that leads naturally toward a deeper look at what life becomes when warmth, colour, and abundance are removed from the equation entirely. Warmth and colour are so deeply embedded in how humans understand life that we often mistake them for requirements rather than conditions. We associate warmth with activity, growth, and comfort. We associate colour with health, diversity and vitality. Green forests, blue oceans, bright animals moving under sunlight. These cues shape our sense of what it means for an environment to be alive. In the Hadal zone, both warmth and colour quietly disappear. Temperature at these depths remains stubbornly low, hovering just above freezing. Unlike the surface, where sunlight drives daily and seasonal fluctuations, the deep ocean is insulated from atmospheric change. Heat from above never reaches it. What warmth exists comes slowly from within the earth itself, diffused and diluted by immense volumes of water. As a result, the Hadal zone exists in a state of near-permanent cold. This cold is not dramatic. There are no sudden freezes, no icy blasts. It is steady, consistent, and unrelenting. For organisms living here, cold is not an event. It is the background condition against which all biological processes must function. Cold changes chemistry. Chemical reactions slow down as temperature drops. Molecules move more slowly. Enzymes, the proteins that drive metabolism, become less efficient. In surface organisms, cold can lead to lethargy, reduced function, or death. In the Hadal zone, life adapts by tuning itself to these slower rates. Hadal organisms often have enzymes that remain active at low temperatures. Their molecular structures are slightly more flexible, allowing reactions to proceed even when thermal energy is limited. This flexibility comes at a cost. These enzymes would become unstable at higher temperatures. Once again, adaptation creates exclusivity. What works here would fail elsewhere. Metabolism in the Hadal zone is slow. There is no rush. Growth takes time. Development unfolds gradually. Energy is conserved wherever possible. Organisms do not burn calories to stay warm. They do not generate internal heat. Their body temperatures match the surrounding water almost exactly. This thermal conformity simplifies some aspects of survival. There is no need for insulation, no need for complex temperature regulation, but it also means that activity is constrained. Sudden bursts of movement are rare. Muscle contraction under cold conditions requires specialized adaptations. Many organisms rely on slow, sustained movements rather than rapid actions. This slowness shapes the entire ecosystem. Food webs operate at reduced speed. Predation events are infrequent. Decomposition proceeds gradually. Organic material persists longer than it would in warmer environments, providing extended opportunities for scavengers and microbes. Microbial activity, though slower, is constant. Bacteria and archaea adapted to cold temperatures break down organic matter, releasing nutrients back into the system. These microbes form the unseen backbone of Hadal ecosystems, quietly recycling energy in a world where little new energy arrives. Cold also affects reproduction. Many deep-sea organisms reproduce infrequently, producing fewer offspring. Developmental stages may last longer. Eggs and larvae, when present, must survive extended periods before reaching maturity. Some species may bypass free-swimming larval stages altogether, reducing exposure to hostile conditions. This slow reproductive strategy makes populations vulnerable to disturbance. Recovery from disruption takes time. A sudden change, whether natural or human-induced, can have long-lasting effects. There is no rapid rebound. Alongside cold, colour fades. Colour depends on light. Pigments absorb and reflect specific wavelengths, producing the hues we see. In the absence of light, colour loses meaning. In the Hadal zone, where sunlight never reaches and bioluminescence is limited and brief, colour provides little advantage. As a result, many Hadal organisms are pale, translucent, or uniformly coloured. Reds, which absorb blue light and appear black at depth, are sometimes retained in shallower deep-sea species, but even these become less relevant in total darkness. In the Hadal zone, pigmentation is often minimal. This absence of colour can feel unsettling to surface observers. It gives organisms a ghost-like appearance, as though they lack substance. But this perception reflects our visual bias, not biological deficiency. Colour is costly. Producing pigments requires energy and resources. If pigments do not serve a purpose, evolution removes them. Transparency goes a step further. By allowing light to pass through their bodies, organisms reduce visibility even when bioluminescence occurs nearby. Transparency also aligns with the gelatinous textures common at depth, reinforcing the theme of softness and flexibility. In this environment, pattern and display lose relevance. There are no visual signals to attract mates or intimidate rivals. Communication shifts to other channels. Chemical cues replace visual ones. Touch replaces sight. Proximity matters more than appearance. This does not mean Hadal life lacks complexity or diversity. It means that diversity expresses itself differently. Differences appear in metabolic pathways, reproductive strategies, sensory systems, and chemical adaptations rather than in coloration or ornamentation. Warmth and colour are also linked in human psychology. Warm colours feel inviting. Cold, pale environments feel empty. The Hadal zone violates these associations. It is cold and colourless, yet inhabited. It supports ecosystems that function continuously, quietly, without spectacle. This challenges a deeply held assumption that life requires warmth and vibrancy to flourish. In reality, life requires stability, compatibility, and energy, even if that energy arrives slowly and unpredictably. The cold also influences how we perceive time. In warmer environments, change is visible. Plants grow quickly, animals move often, seasons shift. In the Hadal zone, change is subtle. Sediments accumulate slowly. Organisms grow over years or decades. A snapshot taken today may look much like one taken years later. This apparent stillness can be misleading. Processes are happening. They are simply happening at a pace that does not announce itself. The absence of warmth slows everything down, but it does not stop it. For researchers, this creates a challenge. Short-term studies may miss important dynamics. Long-term monitoring is difficult at such depths. Understanding life cycles, population changes, and ecosystem responses requires patience measured in decades, not months. Cold also preserves. Organic material decomposes more slowly at low temperatures. In some cases, remains can persist long enough to be discovered long after arrival. This creates feeding opportunities that might not exist in warmer waters, where decomposition is rapid. A single large food fall can sustain a community for extended periods. This preservation extends to chemical signals as well. Dissolved substances linger longer, spreading slowly through the water. Chemical communication may operate over longer timescales, allowing organisms to respond to events that occurred hours or days earlier. The absence of warmth also affects the physical environment. Water density increases slightly at low temperatures, influencing circulation patterns. Currents at depth are slow and stable. There is little mixing. Conditions remain consistent over long periods. This consistency allows for specialization. Organisms adapt to a narrow range of conditions and can rely on those conditions persisting. But it also means that sudden changes can be catastrophic. There is little flexibility built into systems that have never needed it. Colourlessness extends beyond biology into the landscape itself. Trench floors are often composed of fine sediments, muted in tone. There are no reefs, no vegetation, no visually distinct features. Texture replaces colour as the primary defining characteristic. Soft mud, occasional rocks, scattered debris from above. The environment does not draw the eye, it invites stillness. Artificial light introduced by submersibles creates stark contrasts. What was invisible becomes suddenly illuminated. Pale forms appear out of darkness. Sediment particles drift like stars. The effect is dramatic but also misleading. It is a momentary intrusion into a world that does not normally experience illumination. This raises an important consideration. Much of what we think we know about the deep ocean is shaped by how it looks under artificial light. But appearance under these conditions may not reflect natural states. Behaviours may change. Organisms may respond to light as a disturbance. Warmth and colour, or rather their absence, also influence how humans emotionally interpret these environments. Cold, colourless spaces are often described as barren or lifeless. This language carries assumptions that are not supported by evidence. Life here is not absent. It is simply adapted to conditions that do not align with our sensory preferences. There is a tendency to equate vibrancy with importance. Bright ecosystems feel valuable. Subtle ones feel expendable. This bias has consequences. Environments that do not inspire immediate emotional connection are easier to ignore or overlook. Yet the Hadal zone plays a role in global systems. Carbon is stored in its sediments. Nutrients are cycled through its microbial communities. Geological processes interact with biological ones. What happens here affects the planet, even if we rarely think about it. Life without warmth or colour is not diminished life. It is life that has shed unnecessary features. It operates efficiently within strict constraints. It persists quietly. As this understanding settles in, another question begins to form. If life can exist without warmth, without colour, without light, and under crushing pressure, then what we have seen so far may only represent the most visible fraction of what exists. Beneath the sediment, within the cold mud, inside chemical gradients we barely understand, there may be forms of life that never appear on camera at all. Forms that do not move, do not glow, do not announce themselves. And that realization leads naturally toward the question of how much of this world we have actually encountered, and how much remains beyond even our limited glimpses. For all the talk of extremes, mysteries, and unseen life, it is worth slowing down and grounding ourselves in something very simple. What have we actually seen? Not what we suspect, not what we imagine, not what might be hiding just beyond the edge of the light. What has truly been observed, recorded, sampled, and verified in the Hadal zone so far? The answer is both impressive and surprisingly limited. Human interaction with the deepest parts of the ocean is remarkably brief when viewed against the scale of time and depth involved. The Hadal zone has existed for tens of millions of years. Modern exploration of it spans only a few decades, and even within that window, actual time spent observing these depths is measured in hours, not years. Most of what we know comes from a small number of methods: free-falling landers, remotely operated vehicles, autonomous sampling devices, and on very rare occasions crewed submersibles. Each of these tools provides a narrow perspective, shaped by constraints that are easy to overlook. Free-falling landers are among the most commonly used instruments. These devices are dropped from a ship at the surface and sink slowly to the seafloor, guided by ballast and buoyancy. They carry cameras, lights, sensors, and often bait. Once they reach the bottom, they sit and observe for a limited period, recording whatever happens to pass within their field of view. This approach has revealed a consistent pattern across multiple trenches. Within minutes or hours of arrival, scavenging organisms appear. Amphipods are often the first. They detect the bait chemically, even from a distance, and converge steadily. Over time, other creatures may arrive. Small fish, invertebrates, sometimes organisms that defy easy classification. These observations confirm several important facts. Life is present, it is active, it responds to food availability, and it operates according to rules that make sense within this environment. But these observations are also heavily biased. Bait attracts scavengers. It does not attract organisms that feed on microbes, sediment, or dissolved organic matter. It does not attract predators that rely on ambush unless they happen to be nearby. It does not reveal organisms that live buried beneath the sediment or attached to rocks outside the camera's frame. In other words, baited landers show us who responds to food, not who exists overall. Cameras mounted on remotely operated vehicles provide a different perspective. These vehicles can move, explore, and adjust their position. They can examine trench walls, sediment slopes, and specific features of interest. But they are tethered by cables, limiting their range and maneuverability. They are also expensive to operate and rarely deployed at the deepest depths for extended periods. Lighting is another constraint. Powerful lamps are required to see anything at all, but these lights alter the environment. Some organisms flee, others freeze, some are attracted. Behaviour observed under artificial light may not represent natural behaviour. The presence of a vehicle itself introduces noise, vibration, and disturbance. Sampling adds another layer of limitation. Sediment cores provide insight into microbial life and chemical processes. They reveal bacteria, archaea, and other microorganisms living within the seafloor. These samples have shown that life extends deep into the sediment, sometimes meters below the surface, existing in conditions of extreme pressure, low energy, and minimal nutrient flow. But sediment cores are small. They represent tiny volumes of a vast environment. Extrapolating from them requires assumptions that may not always hold. Biological samples collected using nets or traps face similar issues. Many Hadal organisms are fragile. Rapid changes in pressure during retrieval can damage or destroy them. Some species cannot survive decompression at all. What reaches the surface may be incomplete, distorted, or dead before analysis begins. Despite these challenges, certain patterns have emerged from confirmed observations. Amphipods are widespread and abundant in trenches. Multiple species have been identified, many unique to specific trench systems. Their size, behavior, and chemical adaptations have been studied in detail. They represent one of the clearest examples of successful Hadal adaptation. Snailfish have been observed and sampled at remarkable depths. Their presence confirms that vertebrate life extends deeper than once believed. Studies of their tissues have revealed high concentrations of pressure-stabilizing compounds, explaining how their proteins remain functional under extreme compression. Other invertebrates have been recorded as well: polychaete worms, isopods, sea cucumbers adapted to deep sediment feeding. These organisms often exhibit unusual morphologies, elongated bodies, reduced skeletons, and specialized feeding structures. Microbial life has been found everywhere samples have been taken. Bacteria and archaea thrive in Hadal sediments, participating in carbon cycling, nutrient transformation, and chemical processes that influence the broader ocean system. Some of these microbes appear to be endemic, adapted specifically to high-pressure conditions. What we have not seen is just as important. We have not observed complex ecosystems comparable to coral reefs or kelp forests. There are no large, visually dense communities. Life is sparse, distributed, and often solitary. Encounters are infrequent. Activity is subtle. We have not observed large predators patrolling trenches. No equivalent of sharks or whales exists at these depths. Energy constraints make such lifestyles impractical. The food supply cannot support large active hunters. We have not mapped entire trenches in detail. Most seafloor maps are based on sonar data with limited resolution. Fine-scale features remain unresolved. Small habitats, microenvironments, and localized chemical hotspots may exist undetected. We have not observed full life cycles of most Hadal organisms. Reproduction, development, and aging remain poorly understood. We infer these processes from partial evidence and comparisons with shallower relatives. We have not observed how Hadal ecosystems respond to long-term change. Most missions are brief. Long-term monitoring is rare. Seasonal variation, if it exists, is subtle and difficult to detect. Geological events may alter environments dramatically, but capturing these changes in real time is unlikely. There is also the matter of absence caused by methodology. Most exploration focuses on trench floors because that is where landers settle. Trench walls, which can be steep and complex, receive less attention. These vertical environments may host different communities, adapted to different conditions, but they are harder to study. Midwater regions within trenches are also underexplored. Life does not only exist on the bottom. Organisms may inhabit the water column at various depths, moving vertically or remaining suspended. Detecting these organisms requires different tools and approaches. Chemical environments add further complexity. Gradients of oxygen, methane, hydrogen sulfide, and other compounds vary within trenches. Microbial communities respond to these gradients. Larger organisms may cluster around chemical hotspots. Without detailed chemical mapping, these patterns remain speculative. When people hear that only a small percentage of the ocean has been explored, the statement can sound abstract. In the context of the Hadal zone, it is literal. Entire trenches remain unvisited. Others have been visited once or twice. Even the most studied trench has vast areas never seen by any camera. This limited observation shapes public perception. Footage from deep-sea missions circulates widely, giving the impression that we have seen a great deal. In reality, these clips represent rare moments captured under highly specific conditions. Imagine trying to understand a forest by dropping a camera into it for a few hours every decade, always at night, always baited with food, always illuminating a small clearing. You would learn something, but you would miss most of what defines that ecosystem. That is roughly the position we are in with the Hadal zone. The creatures we have seen are real. The data collected is valuable, but it is incomplete by design. The environment itself resists continuous observation. Depth, pressure, cost, and risk all impose limits. This gap between what exists and what we have observed creates space for speculation, but it also demands restraint. It is tempting to fill the unknown with imagined monsters or dramatic narratives. The reality is quieter and more complex. What we know suggests that life in the Hadal zone is resilient, specialized, and deeply adapted. What we do not know likely exceeds what we do. This imbalance is not a failure. It is a reminder of scale. Earth is not fully mapped, not fully catalogued, not fully understood. The deepest parts of the ocean remain one of the few places where this is still true in a very direct sense. As exploration technology improves, the picture will become clearer, but clarity will come slowly. Each new mission adds detail, not completion. And as we sit with what has actually been seen so far, another question naturally arises. If this is what we have observed with our limited tools and brief visits, what remains beyond those limits? Not because it is deliberately hidden, but because our machines, our methods, and our reach still fall short. That question leads inevitably to the tools themselves, and to the very real boundaries imposed not by curiosity, but by engineering. When we talk about exploring the Hadal zone, it is easy to imagine that the primary obstacle is distance, that if only we could go a little deeper, descend a little farther, we would eventually arrive at understanding. But depth is not the real barrier. The true limitation lies in what we can build, what we can protect, and how long our machines can survive in an environment that was never meant to accommodate them. Every piece of technology sent into the Hadal zone is, by definition, temporary. None of it belongs there. None of it is truly compatible with the conditions it encounters. It survives not by adapting, but by resisting, and resistance has a cost. Pressure is the first and most obvious enemy. At extreme depths, even the strongest materials behave differently. Metals compress, polymers stiffen or creep. Microscopic imperfections become critical. A hairline crack that would be irrelevant at the surface can propagate under pressure, turning into catastrophic failure without warning. This means that every component, every joint, every seal must be designed not just to withstand pressure, but to do so repeatedly, predictably, and without fatigue. This is far more difficult than it sounds. The safest shape for resisting pressure is a sphere. That is why crude deep-sea submersibles use spherical pressure hulls. A sphere distributes stress evenly, minimizing weak points, but a sphere is not an efficient shape for observation, movement, or instrumentation. It limits internal space. It restricts window size. It complicates mounting external equipment. Every deviation from a perfect sphere introduces risk. Windows, for example, are among the most vulnerable features. Glass is unusable at these depths. Instead, thick acrylic or specialized composites are used, shaped carefully to deform rather than shatter. Even so, windows are kept small, often only a few centimeters across. The iconic image of a wide viewport looking out into the abyss is largely fiction. In reality, most views are narrow, constrained, and heavily distorted. Uncrewed landers avoid this problem by eliminating pressure hulls entirely. Instead of resisting pressure, they allow water to flood most compartments, protecting only sensitive electronics inside oil-filled housings or small pressure-resistant containers. This approach works, but it introduces other challenges. Cameras and sensors must operate in cold, dark, corrosive conditions. Moving parts become unreliable. Lubricants behave unpredictably. Electronics must function without overheating, without moisture intrusion, and without easy access for repair. Power is another major limitation. Batteries perform poorly in cold environments. Chemical reactions slow down. Capacity drops. Supplying enough energy for lights, cameras, sensors, and communication systems becomes a balancing act. More power means larger batteries. Larger batteries add weight. More weight affects buoyancy and descent speed. Every decision cascades into others. Because of this, most Hadal missions are short. A lander may remain on the seafloor for hours, sometimes a day, rarely longer. Continuous monitoring over weeks or months is extremely difficult. Long-term observatories, common in shallower waters, are nearly impossible at these depths. Communication compounds the problem. Radio waves do not travel through seawater. At depth, communication relies on acoustic signals. These signals are slow, limited in bandwidth, and vulnerable to interference. Sending a single image to the surface can take minutes. Live video is impractical. Control commands are delayed. Real-time decision-making is impossible. This means that many missions operate blindly. Engineers program the lander before deployment, hoping it will encounter something interesting. Adjustments cannot be made on the fly. If the camera angle is wrong, or the lander settles in an uninformative location, the mission may yield little data. Retrieval adds further risk. To return a lander to the surface, ballast weights are released, allowing buoyancy to carry the instrument upward. This process must work flawlessly. If the release mechanism fails, the lander is lost. There is no recovery option. No diver can descend to retrieve it. No tow cable can reach it. The ocean simply claims it. Over the years, many instruments have been lost this way, resting now on trench floors as silent markers of human limitation. Crews are acutely aware of this risk. Every mission involves acceptance of potential loss. Insurance covers some costs, but not data. A lost lander takes its observations with it. Crewing submersibles introduces even stricter constraints. Human-rated vehicles must meet safety margins far beyond those of uncrewed instruments. Redundancy is essential. Systems must fail gracefully. Life support must function reliably for hours under isolation. The psychological demands on occupants are significant. Confined space, limited communication, awareness of total dependence on engineering. Because of these demands, crewed dives to Hadal depths are exceptionally rare. Each one is a major undertaking requiring years of preparation and significant funding. As a result, they provide valuable but extremely limited data. Most of what we know comes from machines that do not think, do not adjust, and do not explore creatively. They record what happens to appear in front of them. Movement itself is constrained. Thrusters struggle under pressure. Sediment stirred up by motion reduces visibility. Navigating uneven terrain in darkness is risky. A misjudged maneuver can trap a vehicle or damage critical components. Trench floors are not smooth plains. They are complex landscapes of slopes, ridges, and unstable sediment. Autonomous navigation systems are improving, but they remain limited. GPS does not work underwater. Positioning relies on acoustic triangulation, which becomes less precise with depth and distance. Knowing exactly where a vehicle is, relative to the seafloor, is difficult. Sampling is equally challenging. Collecting biological specimens without destroying them requires delicate manipulation. Robotic arms must operate under pressure, cold, and limited visibility. Fine movements are hard to control. Fragile organisms may disintegrate under mechanical stress or pressure change during ascent. Even when samples are retrieved intact, interpretation is complicated. Bringing Hadal organisms to surface pressure alters them. Some cellular structures degrade. Chemical balances shift. What we analyze in the lab may not perfectly reflect conditions in situ. These limitations shape our understanding. we tend to study what our machines can detect. Larger organisms, scavengers drawn to bait, microbes present in sediment cores. Life forms that fit within our sampling methods become known. Others remain invisible. There may be organisms that avoid bait entirely, species that live permanently within sediment layers, forms that are too small, too fragile, or too chemically subtle to register on our instruments. Entire ecological interactions may occur beyond our detection thresholds. This is not because they are rare, it is because our tools are blunt. Cost plays a decisive role. Deep-sea exploration is expensive. Ship time, specialized crews, custom-built equipment. Each mission requires significant investment. Funding is limited. Priorities compete. As a result, Hadal exploration proceeds slowly, episodically, often driven by individual research programs rather than sustained global efforts. Maintenance is another issue. Equipment that returns from extreme depths often requires extensive refurbishment. Components must be inspected for micro-damage, seals replaced, electronics tested. The turnaround time between missions can be long. This slows progress further. There is also the problem of scale. Trenches are vast. A single dive covers a tiny fraction of available area. Even if technology were perfect, it would take decades to map these environments comprehensively. With current limitations, full coverage is not realistic in the near future. This does not mean progress has stalled. New materials are being developed, improved sensors, better batteries, smarter autonomous systems. Advances in machine learning allow for better pattern recognition in limited data. Miniaturization enables more instruments to be deployed at once, but each improvement reveals new challenges. Increased data volume strains communication. More complex systems introduce new failure points. Deeper dives push materials closer to their limits. There is no final solution, only incremental gains. The ocean does not yield easily to engineering. It does not reward ambition with shortcuts. It demands patience, redundancy, and acceptance of loss. In this sense, the Hadal zone enforces a kind of discipline. It reminds us that technology is not omnipotent, that curiosity must operate within physical constraints, that some environments will always resist full access. This resistance shapes the nature of discovery. What we learn arrives slowly, piecemeal, often unexpectedly. Each observation feels provisional. Each conclusion remains open to revision. And this uncertainty leaves space. Space for unanswered questions. Space for unobserved life. Space for possibilities that exist not because we imagine them, but because our tools have not yet been able to confirm or deny them. As long as our machines remain limited, so too does our knowledge. And in that gap between environment and capability, the Hadal zone continues to exist largely on its own terms, quietly hosting processes and forms that do not depend on being seen. Which leads naturally to the next consideration. If our machines cannot reach everywhere, cannot stay long, and cannot observe continuously, then there are entire regions of the Hadal zone that remain effectively untouched. Not because they are hidden, but because they lie just beyond the reach of our current reach. And in those untouched spaces, time continues to pass, and life continues to unfold without interruption. It is tempting to assume that unexplored places persist because no one has bothered to look. That if an area remains unknown, it must be because curiosity has not yet arrived. In the case of the Hadal zone, the opposite is true. Curiosity has been present for decades. What has been missing is not interest, but access. The Hadal zone remains unexplored not because it is ignored, but because it actively resists exploration at nearly every level. Depth, pressure, scale, cost, time, and risk all combine to slow progress in ways that are difficult to overcome, even with modern technology. One of the most significant reasons is sheer geography. The Hadal zone does not form a single continuous region. It exists as a collection of deep trenches scattered across the world's oceans. These trenches are often long and narrow, sometimes stretching for thousands of kilometres, but only a few kilometres wide. They are isolated from one another, separated by vast areas of shallower seafloor that function as barriers to both life and exploration. Reaching a trench is not as simple as sailing to a location and deploying equipment. Many trenches lie far from coastlines in remote parts of the ocean. Reaching them requires long voyages, favourable weather, and significant logistical planning. Ship time alone represents a major investment, and deep-sea research vessels are limited in number. Once a trench is reached, exploration does not proceed quickly. Descent to Hadal depths can take hours. Ascent takes even longer. A single deployment may consume an entire day for only a few hours of observation on the seafloor. Weather conditions at the surface can delay or cancel operations entirely. Equipment failures can end missions before they begin. Then there is the matter of scale. Even when a lander reaches the bottom of a trench, it observes only a tiny area. A camera's field of view may cover a few square meters in an environment that stretches for thousands of square kilometers. Mapping such an area comprehensively would require an enormous number of deployments, each costly and time-consuming. Sonar mapping helps, but sonar has limitations. At extreme depths, resolution decreases. Fine details are lost. Sonar provides shapes and gradients, not textures or biological information. It can tell us where the trench is, how deep it is, and what its broad features look like, but it cannot tell us what lives there or how organisms interact with the environment. Even the most detailed maps of trenches are coarse compared to maps of land or shallow seafloor. Many features remain unresolved. Small ridges, sediment flows, chemical seeps, and microhabitats may exist undetected, shaping ecosystems in ways we do not yet understand. Time is another major factor. Deep-sea exploration does not benefit from rapid iteration. Each mission requires extensive planning, testing, and coordination. Instruments must be designed, built, and tested under simulated pressure conditions. Crews must be trained, contingencies must be prepared. After a mission, data analysis takes time. Samples are examined, footage is reviewed, results are published, lessons are learned. Only then can the next mission be planned. This cycle can take years. As a result, progress accumulates slowly. Knowledge grows incrementally rather than exponentially. Each new observation adds a piece to the puzzle, but the puzzle itself remains vast. Funding constraints reinforce this slow pace. Deep-sea research competes with many other scientific priorities: space exploration, climate monitoring, medical research, renewable energy. Funding agencies must make choices. The Hadal zone, remote and largely invisible to the public, often struggles to justify sustained investment. This is not because it lacks importance, but because its relevance is indirect. Processes occurring at depth influence global systems, but those connections are subtle and difficult to communicate. The benefits of exploration are long-term and foundational rather than immediate. Risk also plays a role. Every deep-sea mission carries the possibility of equipment loss. Instruments may fail, landers may not return, submersibles may encounter unexpected conditions. While human safety is prioritized, the financial risk remains significant. This risk encourages caution. Missions are conservative in scope. Experimental approaches are tested slowly. Bold exploration is tempered by practical concerns. This reduces the chance of catastrophic failure, but it also limits discovery. There is also the problem of endurance. The Hadal zone does not reveal its secrets quickly. Many processes unfold over long timescales. Biological interactions may be infrequent. Geological changes may occur sporadically. Capturing these dynamics requires long-term monitoring, which is extremely difficult at such depths. Permanent observatories, common in shallow marine environments, are nearly impossible to maintain in trenches. Power supply, data transmission, and maintenance challenges compound with depth. As a result, Most observations are snapshots rather than continuous records. This creates gaps in understanding. We know what happens when a lander arrives with bait. We know what happens when a camera illuminates a small area for a few hours. We do not know what happens the rest of the time. We do not know how organisms behave when undisturbed. We do not know how communities change over months or years. Another factor is methodological bias. Exploration tools are designed with certain expectations. Cameras look outward. Samplers collect sediment or visible organisms. Sensors measure specific chemical parameters. These tools are effective for detecting what we anticipate, but they may miss phenomena we have not yet imagined. If a form of life does not move, does not glow, does not respond to bait, and does not significantly alter chemistry in obvious ways, it may escape detection entirely. Life could exist in forms or states that our instruments are not tuned to observe. This is not hypothetical. In other extreme environments, such as deep subsurface rock or polar ice, life was discovered only after methods were adapted to look for it. Before that, it went unnoticed. The Hadal zone may host similar surprises. Human perception also plays a role. The deep ocean lacks the visual drama that often drives exploration. There are no sweeping vistas, no dramatic colour contrasts, no obvious landmarks. Footage can appear monotonous to untrained eyes. Subtle differences matter, but they are easy to overlook. This affects how discoveries are communicated and valued. A single unusual organism may represent a major scientific finding, but it does not always capture public attention. Without public interest, funding and momentum can wane. There is also a psychological barrier. Depth evokes discomfort. The idea of being crushed by pressure, isolated from the surface beyond rescue, triggers instinctive unease. This affects not only potential explorers, but also how society perceives deep-sea research. It feels risky, remote, and abstract. As a result, fewer people pursue careers focused on Hadal exploration. Expertise is limited. Knowledge accumulates slowly. International coordination adds complexity. Trenches cross political boundaries. Some lie within national exclusive economic zones. Others lie in international waters. Research requires permits, agreements, and collaboration across borders. This coordination can be time-consuming and politically sensitive. Data sharing varies. Some findings remain unpublished for years. Others are restricted. Building a comprehensive global picture becomes more difficult when information is fragmented. All of these factors reinforce one another. Depth increases cost. Cost limits frequency. Limited frequency reduces data. Limited data increases uncertainty. Uncertainty discourages investment. The cycle continues, and yet exploration continues. Each new mission pushes boundaries slightly. Each new instrument extends reach a little farther. Each discovery challenges assumptions and justifies further effort. Progress is slow, but it is real. The Hadal zone remains unexplored not because it is unknowable, but because it demands patience on a scale that modern systems struggle to accommodate. It operates on geological time, while research operates on funding cycles. It requires endurance, while institutions favour efficiency. This mismatch does not mean exploration will stop. It means it will proceed cautiously, selectively, and incompletely for the foreseeable future. And in that incompleteness lies something important. Unexplored does not mean empty. It means active, ongoing, independent of observation. Life continues to exist, adapt, and interact regardless of whether it is seen. Geological processes reshape trenches. Chemical gradients shift. Ecosystems respond. The Hadal zone does not wait for us. As we acknowledge why so much of it remains beyond our reach, another realization takes shape. The absence of observation leaves room not just for ignorance, but for interpretation. For hints and traces that suggest more than we can currently confirm. And it is those hints, faint and indirect, that begin to draw attention next. When exploration reaches its limits, certainty gives way to suggestion. Not guesses, not fantasies, but small irregularities that refuse to fit neatly into what we already know. In the Hadal zone, these irregularities appear often, not as dramatic encounters or unmistakable discoveries, but as hints. Data points that feel slightly off, footage that raises more questions than it answers, measurements that make sense individually but not together. This is the space where much of our understanding of the deep ocean currently lives. Most deep-sea missions are designed with specific goals: measure pressure, record temperature, observe forcing scavengers, collect sediment samples. These objectives shape what instruments look for and how data is interpreted. When something appears outside those expectations, it can be difficult to classify and even harder to confirm. One of the most common sources of unconfirmed encounters comes from video footage. Cameras lowered into trenches sometimes capture movement at the edge of the frame. A shape passes briefly through the light and disappears before it can be resolved. A disturbance in sediment suggests something moved nearby, but nothing remains in view. These moments are often dismissed as artifacts, a current, a shadow, a reflection. Sometimes that is exactly what they are, but not always. The challenge is that deep-sea footage is inherently limited. Lighting is artificial and directional. The field of view is narrow. The camera itself may be moving slightly due to currents or equipment adjustment. Compression artifacts, low frame rates, and grainy resolution all reduce clarity. When something unexpected appears, it is rarely captured cleanly. Scientists are cautious by necessity. Extraordinary claims require extraordinary evidence. A single ambiguous clip is not enough to establish the existence of an unknown organism, so these encounters remain unconfirmed, noted but not emphasized. Still, patterns emerge. Across multiple missions in different trenches, similar anomalies appear. Shapes that do not resemble known species. Movements that do not match the behavior of organisms commonly observed at those depths. Signals detected by sensors that do not align with expected physical processes. Acoustic data provides another source of intrigue. Hydrophones placed in deep water record sounds that travel vast distances. Most of these sounds can be traced to known sources: earthquakes, ice movement, distant storms, marine mammals, human activity. But occasionally, recordings include signals that defy easy explanation. These signals are often low frequency, sustained and irregular. They do not resemble known biological vocalizations, but they also do not match typical geological noise. In many cases, they are written off as unknown seismic activity or instrument interference. Without corroborating data, classification is difficult. The key point is not that these sounds represent unknown creatures. It is that the deep ocean produces signals we do not yet fully understand. Chemical anomalies add another layer. Sediment cores and water samples sometimes reveal unexpected concentrations of certain compounds. Spikes in methane, unusual distributions of organic molecules, traces of metabolic byproducts that suggest biological activity beyond what visible organisms would account for. Microbial life is often the explanation. Bacteria and archaea can produce a wide range of chemical signatures, but in some cases the scale or pattern of these anomalies raises questions. Are there microbial communities we have not yet identified? Are there metabolic pathways operating under conditions we do not fully understand? Again, these are not confirmations, they are prompts. Physical traces appear as well. Sediment disturbances that do not align with known current patterns. Tracks or impressions that suggest movement across the seafloor. These marks are often subtle and quickly erased by slow sediment flow. Capturing them requires timing and luck. When such traces are found, interpretation is cautious. A small landslide, equipment disturbance, biological activity from known organisms behaving in unfamiliar ways. Without direct observation, certainty remains elusive. There is also the issue of scale mismatch. Our instruments are designed to detect objects within certain size ranges. Cameras capture what fits within their frame. Nets collect organisms above a certain size threshold. Sensors detect chemical changes above background levels. Anything smaller, slower, or more diffuse may go unnoticed. Life does not need to be large or active to be significant. Entire ecosystems can exist at microbial scales. Interactions can occur chemically rather than physically. If such systems dominate parts of the Hadal zone, they would leave few obvious traces. This possibility complicates interpretation of absence. Just because we have not seen something does not mean it is not there. It may simply operate outside our detection window. There are also historical hints worth mentioning. Early deep-sea expeditions using far cruder equipment occasionally reported findings that could not be fully explained at the time. Organisms recovered damaged or incomplete, measurements that did not match expectations. These reports were often set aside due to uncertainty or lack of replication. Modern technology allows us to revisit some of these questions, but not all. Some locations remain inaccessible. Some equipment limitations persist. Some observations remain singular. Human psychology plays a role here as well. There is a fine line between healthy curiosity and projection. The unknown invites imagination. It is easy to fill gaps with speculation, especially in environments as remote and hostile as the Hadal zone. This is why scientific caution is essential. It protects against self-deception. At the same time, excessive conservatism can slow recognition of genuinely novel phenomena. Many major discoveries began as anomalies, signals that did not fit existing models, data that was initially dismissed as error. The balance between skepticism and openness is delicate. In the deep ocean, that balance is constantly tested. Instruments fail. Conditions are unpredictable. Replication is difficult. When something unusual appears, it may take years or decades before it can be investigated again. This creates a kind of scientific limbo. Observations are recorded, discussed quietly, and set aside until more data becomes available. Some are eventually explained, others remain unresolved. There is also the question of bias in reporting. Scientific publications favour clarity and confirmation. Ambiguous findings are harder to publish. They do not fit neatly into established frameworks. As a result, hints and anomalies may be underrepresented in the literature, discussed informally rather than formally. This does not mean they are ignored. It means they wait. In recent years, improvements in data analysis have allowed researchers to revisit old datasets. Machine learning techniques can identify patterns previously overlooked. Reanalyzing acoustic recordings, chemical data, and video footage sometimes reveals consistencies that were not obvious before. This process has already led to the identification of new species and behaviours in shallower deep-sea environments. It is reasonable to expect similar outcomes in the Hadal zone as tools improve. Still, confirmation remains slow. Every hint must be followed by targeted observation. Every anomaly requires context. In an environment where access is limited, gathering that context takes time. It is important to emphasize what these hints do and do not represent. They are not evidence of hidden monsters or dramatic unknown predators. The conditions of the Hadal zone make such creatures unlikely. Energy constraints limit size and activity. The environment favors efficiency, not spectacle. What these hints suggest instead is complexity. Layers of biological and geological interaction that we have not yet fully described, life strategies that do not announce themselves, processes that operate quietly, leaving subtle traces rather than obvious signs. This quiet complexity aligns with everything else we know about the Hadal zone. It is not a place of sudden events, it is a place of persistence. When something unexpected appears, it is usually understated. A chemical gradient slightly out of range, a movement that does not repeat, a sound that does not recur. These moments are easy to miss, easy to dismiss, but taken together, they point toward a reality that is richer than our current models account for. The Hadal zone is not hiding secrets in the dramatic sense. It is simply not optimized for human observation. Its signals are faint, its rhythms are slow, its inhabitants do not interact with us in ways that demand attention. Understanding this requires patience and restraint. It also requires accepting uncertainty as part of knowledge rather than a failure of it. Not knowing is not the same as ignorance. It is an honest acknowledgement of limits. As exploration continues, some of these hints will be resolved. An anomaly will be traced to a known process. An unfamiliar shape will be identified as a life stage of a known species. A strange signal will be linked to geological activity. Others may persist. They will remain in datasets, footnotes, and quiet conversations among researchers. They will serve as reminders that the deep ocean still operates beyond our full comprehension. And this unresolved space has consequences. It shapes how we think about evolution, adaptation, and the range of possible life strategies. It challenges assumptions about where life can exist and how it behaves under extreme conditions. As these hints accumulate, attention naturally shifts toward a broader question. Not about specific encounters, but about the process that produces them. About how evolution behaves when survival depends on enduring conditions that push biology to its limits. That question leads deeper still, beyond individual observations, into the mechanisms that shape life at the edge of what is possible. Evolution is often explained using examples that are easy to visualize. Faster animals outrunning predators, better camouflage blending into forests, stronger beaks cracking harder seeds. These stories are useful, but they come from environments where life has room to maneuver, where choices exist, where multiple strategies can coexist and compete. At the edge of survival, evolution behaves very differently. In the Hadal zone, evolution is not about improvement in the usual sense. It is about tolerance, not speed, not intelligence, not dominance, but the ability to remain functional under conditions that are relentlessly unforgiving. Here, the environment does not reward innovation unless that innovation reduces strain, saves energy, or prevents failure at the most basic biological level. Pressure does not negotiate, darkness does not ease, cold does not relent, scarcity does not fluctuate dramatically. These conditions are constant enough that evolution has little incentive to experiment widely. Instead, it narrows its focus. Traits that work persist. Traits that do not are eliminated quickly and without ambiguity. At the edge of survival, there is no advantage to being slightly better. There is only advantage to being compatible. This changes the shape of natural selection. In more forgiving environments, evolution can favour traits that provide marginal benefits. A little faster, a little stronger, a little brighter. Over time, these small advantages accumulate. In the Hadal zone, marginal improvements often do not matter. Either a protein functions under pressure or it does not. Either a membrane remains stable or it fails. Either a metabolic pathway operates at low temperature or it stalls. This creates sharp thresholds rather than gradual gradients. Once those thresholds are met, further refinement may slow dramatically. There is little incentive to optimize beyond sufficiency. Energy saved by eliminating unnecessary complexity becomes more valuable than energy spent refining performance. This is why many Hadal organisms appear simplified by surface standards, not primitive but pared down. Structures that do not directly support survival under extreme pressure and low energy availability tend to disappear over evolutionary time. Eyes reduce or vanish. Pigmentation fades. Fast twitch muscles become less relevant. Elaborate skeletal systems lose value. What remains are systems that maintain internal stability. Evolution here favours robustness over versatility. Another defining feature of evolution at this edge is conservatism. Once a lineage acquires a set of adaptations that allow it to function in the Hadal zone, deviation becomes risky. A mutation that slightly destabilizes a pressure-adapted protein may be fatal. A change that increases metabolic demand may not be sustainable. As a result, evolutionary change may slow once a workable configuration is achieved. This does not mean evolution stops. It means it proceeds cautiously. Changes that persist tend to be those that fine-tune existing systems rather than reinvent them. Small adjustments in enzyme structure, subtle shifts in membrane composition, slight changes in reproductive timing. These refinements occur over long timescales. Isolation reinforces this pattern. Each trench functions as a biological island. Populations are separated by distances and depth gradients that are difficult to cross. Gene flow between trenches is limited. This isolation allows lineages to diverge, but within strict boundaries imposed by the environment. The result is not explosive diversification, but parallel adaptation. Similar body plans evolving independently in different trenches. Similar metabolic strategies appearing in unrelated lineages. Convergence driven by constraint rather than opportunity. Evolution at the edge often produces resemblance, not variety. This can be misleading. To a casual observer, organisms from different trenches may look alike. Pale, soft-bodied, simplified. It would be easy to assume they are closely related. Genetic studies often reveal otherwise. These similarities arise not from shared ancestry, but from shared necessity. When only a narrow range of solutions works, evolution repeatedly finds those solutions. Another important aspect of edge evolution is tolerance over performance. In surface environments, organisms often push performance limits: maximum speed, maximum strength, maximum output. In the Hadal zone, pushing limits increases risk. Systems that operate close to failure thresholds are vulnerable to even small disturbances. Evolution therefore favours operating margins. Proteins are stabilised beyond minimum requirements. Membranes remain fluid across narrow but reliable ranges. Metabolic pathways are buffered against fluctuations. These redundancies reduce efficiency but increase reliability. Energy efficiency still matters, but not at the expense of stability. This trade-off explains why many Hadal organisms have low metabolic rates. High-output systems consume energy quickly and generate waste heat. In cold, energy-poor environments, such systems are unsustainable. Slower metabolism reduces demand and allows organisms to survive longer between feeding opportunities. Longevity becomes a viable strategy. When reproduction is infrequent and development slow, longer lifespans help maintain populations. Individuals may persist for years or decades, contributing multiple times to reproduction over long periods, rather than producing large numbers of offspring quickly. This strategy contrasts sharply with many surface species, where high mortality favours rapid reproduction. At the edge, survival itself is the limiting factor, not competition. Evolution also behaves differently in terms of risk. In more benign environments, risky strategies can pay off. A mutation that increases speed may lead to more food and higher reproductive success, even if it increases injury risk. In the Hadal zone, risky strategies are rarely rewarded. Injury may not heal. Recovery resources are scarce. Failure is often final. As a result, behaviours and traits tend to be conservative. Movements are deliberate. Energy expenditures are calculated. Novel behaviours spread slowly, if at all. This does not imply a lack of complexity. Complexity exists, but it is often internal rather than external. Biochemical networks capable of functioning under extreme pressure. Cellular repair mechanisms tuned for cold conditions. Genetic regulation that maintains stability despite slow reaction rates. From the outside, these organisms may appear simple. On the inside, they are anything but. Evolution at the edge also blurs distinctions between living and non-living processes. In the Hadal zone, microbial communities often dominate energy cycling. These microbes operate close to thermodynamic limits. Chemical reactions proceed slowly, driven by minimal energy differences. Life here exists at the boundary between chemistry and biology. This raises interesting questions about how life began and how it might exist elsewhere. If life can persist under these conditions on Earth, then the range of environments capable of supporting life may be broader than previously assumed. Not more energetic, but more stable. Not warmer, but more consistent. Not brighter, but chemically active. The Hadal zone becomes a natural laboratory for studying minimal life. Another feature of evolution at this edge is delayed feedback. In fast-changing environments, selection pressures shift quickly. Populations respond over short timescales. In the Hadal zone, environmental conditions change slowly. Geological processes operate over thousands or millions of years. Climate influence is indirect and delayed. This means that evolutionary responses may lag behind changes. A disturbance may occur, but its effects on populations may unfold over generations. Recovery may take centuries. Such long feedback loops make evolutionary dynamics difficult to observe directly. They also make systems sensitive to rapid change. When change happens faster than adaptation can occur, resilience breaks down. This is particularly relevant when considering human impact. Evolution at the edge is tuned to stability. Sudden inputs of pollutants, temperature changes, or physical disturbance may exceed adaptive capacity. Traits that evolved to handle slow geological shifts may not cope with abrupt alterations. Understanding this vulnerability requires acknowledging that resilience is context-dependent. The Hadal zone is resilient to pressure, darkness, and cold. It may not be resilient to rapid chemical or physical disruption. There is also an important philosophical implication. At the edge of survival, evolution is stripped of drama. There is no arms race, no escalating competition, no flamboyant display. What remains is persistence. Life continues not because it is exceptional, but because it is adequate. This challenges narratives that equate evolution with progress. In the Hadal zone, evolution does not aim upward. It aims inward, toward compatibility, toward balance, toward existing without drawing attention. These organisms are not on a path toward complexity as we define it. They are on a path toward endurance. From a human perspective, this can feel anticlimactic. We expect extremes to produce extremes, monsters, giants, super predators. Instead, the edge produces subtlety, precision, quiet persistence. But this subtlety is profound. It demonstrates that life does not need favourable conditions to exist. It needs stable ones. It does not need abundance. It needs consistency. It does not need to dominate its environment. It needs to fit within it. As attention stays with this idea, another realization emerges. If evolution can produce viable life strategies under such restrictive conditions, then the boundary of what we consider possible may be misplaced. The Hadal zone may not represent the extreme limit of life, but one expression of it. And that thought naturally invites a shift in perspective, away from what we have already observed and toward what may still exist beyond our current understanding, not as fantasy, but as a logical extension of evolutionary possibility in an environment that continues to operate beyond our reach. When people hear the phrase, "what might still be hiding down there," it often triggers images shaped by fiction rather than biology. Oversized predators, ancient survivors, creatures built for spectacle. These ideas persist because the deep ocean feels distant and unknowable, and the human mind tends to fill unknown spaces with exaggeration. But the reality of what may still exist in the Hadal zone is both quieter and in many ways more unsettling. What might still be hiding down there is not hiding in the sense of avoidance. It is hidden because the environment itself filters what can be seen, what can be reached, and what can be recognized as life at all. The first category of unseen life is the simplest to imagine. More of what we already know. Every trench explored has revealed species that were previously unknown. Not radically different organisms, but variations shaped by isolation. New amphipods, new worms, new microbial strains. Each trench acts as an evolutionary laboratory, producing local adaptations over millions of years. Given how few trenches have been explored, it is almost certain that many species remain undescribed. These organisms may resemble known forms closely enough that, without genetic analysis, they would be mistaken for familiar species. Their differences may lie in enzyme structure, membrane chemistry, reproductive timing, or pressure tolerance. From a distance, they may look the same. At the molecular level, they may be distinct. This kind of hidden diversity is easy to underestimate because it lacks visual drama. Yet it represents a significant portion of Earth's biodiversity, existing entirely outside human awareness. Beyond this lies a second category, life that behaves differently enough to avoid our current methods of detection. Most deep-sea exploration relies on movement, light, and reaction. Cameras capture organisms that swim or crawl into view. Bait attract scavengers. Sensors detect chemical changes above certain thresholds. Anything that does not move much, does not respond to bait, and does not significantly alter its surroundings may go unnoticed. Life does not need to be mobile to exist. There may be organisms that live almost entirely within sediments, interacting slowly with their environment. Communities that spread not through movement, but through gradual growth. Forms of life that exist as thin layers, films, or networks, neither clearly plant nor animal by surface definitions. Microbial life already occupies this category, but it may not be limited to microbes as we currently define them. Multicellular life could exist in forms that do not resemble animals in any familiar way. Structures optimized for chemical exchange rather than locomotion. Bodies shaped to maximize surface contact with sediment rather than interaction with open water. Such life would be extremely difficult to detect with cameras or nets. It would not react to light. It would not chase food. It would not announce its presence. A third category involves scale. Our exploration tools are optimized for certain size ranges. Organisms too small to be resolved by cameras appear as noise. Organisms too diffuse blend into the background. Organisms too fragile may disintegrate before they can be identified. In extreme environments, scale often shifts. Large complex structures are costly. Smaller, simpler systems may dominate. Entire ecosystems may operate at scales that feel insignificant to human perception, but are ecologically complete. Life may exist in gradients rather than discrete bodies, distributed systems rather than individuals, networks of interacting components that function collectively rather than independently. If such systems exist, they would challenge our definitions of what it means to encounter an organism. Another possibility lies in chemistry. Life in the Hadal zone already operates near thermodynamic limits. Energy inputs are minimal. Reactions are slow. It is plausible that metabolic pathways exist that we have not yet characterized. Pathways that use uncommon substrates. Processes that proceed so slowly they leave faint signatures. Some life may exist in a state that resembles dormancy more than activity, activating only when conditions align. Others may operate continuously, but at rates so low they are difficult to distinguish from background chemistry. Detecting such life requires methods that do not yet exist, or are not yet deployed at these depths. There is also the question of transitional forms. Evolution does not always produce neat categories. There may be organisms that blur boundaries between microbial and multicellular life. Systems that challenge classification. Entities that do not fit comfortably into plant, animal, or fungus. In other extreme environments, such boundary-challenging life has already been found. The deep ocean may host similar examples, adapted specifically to high pressure and low energy availability. Another overlooked factor is time. Most observations capture moments, a few hours, a day at most. But biological events may occur on much longer cycles. Reproduction might happen once every few years. Growth may be imperceptible over short timescales. Behavior may change in response to rare events such as large food falls or geological disturbances. Life that is active only occasionally may never be seen during a brief visit. its presence would be inferred only indirectly, if at all. This introduces the idea of episodic ecosystems, communities that remain mostly inactive, conserving energy, then briefly become active when conditions allow. Afterward, they return to dormancy. Such systems would be nearly invisible to conventional exploration. There is also vertical complexity. Most attention focuses on trench floors, but trenches are three-dimensional environments. Water columns extend upward for kilometres. Walls rise steeply. Chemical gradients vary with depth. Life may occupy narrow bands where conditions align just right. Organisms adapted to these bands may never encounter landers placed on the bottom. They may drift above, move laterally, or remain attached to walls that are rarely explored. This vertical partitioning could host entire communities that remain unseen simply because we are looking in the wrong place. Then there is the influence of geology. Subduction zones are active. Fluids move through rock. Minerals dissolve. Gases escape. These processes create localized chemical environments that may support life independent of surface input. Life associated with these processes may exist deep within sediments or rock fractures, emerging only occasionally, if at all. Such life would not appear on cameras. It would be detected only through subtle chemical or thermal anomalies. This raises the possibility that some life in the Hadal zone exists largely outside the water column itself, embedded within the earth. Perhaps the most important thing to recognize is that hiding implies intent. Life does not hide. It occupies niches. If those niches do not intersect with our instruments, life remains unseen. The deep ocean has already shown that assumptions based on surface experience fail at depth. Fish were not supposed to exist there. Multicellular life was expected to thin out, yet it persists. Given that history, it would be surprising if everything that exists had already been observed. At the same time, restraint is necessary. The Hadal zone is not a place of unlimited possibility. Energy constraints are real. Pressure imposes strict limits. The environment favours subtlety over extravagance. Whatever exists down there is likely shaped by these constraints. That means no giants, no fast-moving apex predators, no ecosystems built on abundance. What remains possible is persistence, specialisation and efficiency. What might still be hiding down there is not something waiting to be discovered for shock value. It is something quietly continuing, indifferent to whether it is ever seen. This perspective shifts the emotional tone of exploration. The unknown is not threatening. It is simply unobserved. It does not challenge us. It ignores us. And that indifference is perhaps the most striking feature of the Hadal zone. Life there does not depend on human presence. It does not respond to our curiosity. It does not adapt to our schedules. As technology improves, some of what is hidden will be revealed. New species will be described. New processes will be identified. But the unknown will never disappear entirely. Because the Hadal zone is vast. Because exploration is slow. And because life does not announce itself. This leads naturally to a broader reflection. Not about specific organisms, but about what this hidden world represents in relation to humanity, about why places like this matter, even if we never fully understand them. And that reflection brings attention toward the way the Hadal zone quietly reshapes our sense of knowledge, humility, and scale. For much of human history, the unknown was assumed to be temporary. A blank space on a map meant something had not yet been reached, not something fundamentally beyond reach. Mountains were climbed, deserts crossed, poles reached. Even space, once the ultimate symbol of distance and danger, became a place humans could briefly inhabit. Progress reinforced a quiet confidence that with enough time and technology, every corner of Earth would eventually yield. The deep ocean challenges that confidence in a way few other places do. It does not resist exploration with hostility or spectacle. It does not present dramatic barriers or visible danger. Instead, it humbles through indifference, through scale, through conditions that do not bend no matter how advanced our tools become. The Hadal zone exists beneath everything familiar, beneath shipping routes, beneath coastlines, beneath the rhythms of weather and climate that dominate human attention. Entire civilizations have risen and fallen without ever touching it. Even now, daily life continues almost completely unaware of what lies kilometers below. This disconnect matters. Human knowledge is shaped by proximity. We understand what we can visit, manipulate, and observe repeatedly. The deep ocean remains distant not only physically, but experientially. We cannot walk there. We cannot stay there. We cannot sense it directly. Every interaction is mediated through machines, data, and interpretation. This creates a gap between presence and understanding. We know the Hadal zone exists. We know its depth. We know some of its inhabitants. But knowing something exists is not the same as knowing it intimately. The deep ocean remains abstract in a way that forests, cities, and even space stations do not. Scale is the first lesson in humility. When viewed from the surface, the ocean feels vast, but its depth is easy to underestimate. 8 kilometers of water compresses perception. On land, 8 kilometers is a long drive. In the ocean, it is a vertical descent into a fundamentally different world. A world where pressure alone would destroy unprotected human bodies instantly. No amount of confidence changes that fact. We often imagine technology as an extension of ourselves, tools that allow us to go where we cannot. But the deep ocean reminds us that tools are temporary visitors. They survive only as long as materials hold, as long as seals remain intact, as long as systems do not fail. When a lander is lost, it is not because the ocean acted aggressively. It is because the environment continued to behave exactly as it always does. Pressure did not increase. Cold did not intensify. Darkness did not deepen. The machine failed because it was never meant to belong there. This realization reframes exploration. In many environments, humans arrive and reshape. We build infrastructure, we alter landscapes, we introduce noise, light, and movement. In the Hadal zone, our presence is fleeting and fragile. We cannot reshape it. We cannot occupy it. We cannot even observe it continuously. The deep ocean allows us to look, briefly, and then insists we leave. There is also humility in how little of it we need to affect. Human influence has reached the deepest trenches without intention. Microplastics have been found in sediments. Chemical signatures of industrial activity appear in unexpected places. The Hadal zone does not exist outside global systems. It is connected quietly to everything above. This reveals a paradox. We cannot easily explore or inhabit the deep ocean, yet we can influence it unintentionally. Our reach extends further than our understanding. We change environments we barely know. That imbalance is humbling in a different way. The deep ocean also humbles through patience. Human timelines are short. Projects are measured in years, careers in decades, civilizations in centuries. The processes shaping trenches operate over millions of years. Sediments accumulate slowly. Evolution proceeds cautiously. Geological forces reshape the seafloor over spans that dwarf human history. When we observe the Hadal zone, we are glimpsing moments within processes that began long before humans existed and will continue long after. This perspective reduces the sense of centrality. The deep ocean does not revolve around human presence. It does not respond to our curiosity. It does not accelerate its processes for our convenience. It exists on its own schedule. There is also humility in the limits of explanation. For all our models and measurements, many aspects of the Hadal zone remain unresolved. Not because we lack intelligence, but because data is sparse, because observation is difficult, because replication is rare. In many scientific fields, uncertainty shrinks as data accumulates. In the deep ocean, uncertainty persists longer. Hypotheses remain provisional. Conclusions are cautious. Knowledge advances slowly. This challenges the expectation of rapid understanding. It also encourages restraint. The deep ocean reminds us that not knowing is not failure. It is a condition of engaging with environments that exceed our reach. Accepting uncertainty becomes part of responsible inquiry. Emotionally, this can be uncomfortable. Humans are accustomed to mastery, to naming, categorizing, controlling. The Hadal zone resists this impulse. It remains largely unnamed at the level of daily experience. Many of its species lack common names. Many features lack detailed maps. This absence of familiarity creates distance, and yet that distance has value. It preserves a sense of scale that is otherwise easy to lose. In a world increasingly shaped by human activity, the deep ocean stands as a reminder that Earth is not fully domesticated, that there are still places where natural processes dominate. This does not make the deep ocean pristine in the sense of untouched. It makes it autonomous. Autonomy is humbling. It means accepting that some parts of the planet do not revolve around human needs or narratives. They exist regardless of whether they are useful, visible, or understood. There is also humility in comparison. We often compare our technological achievements to natural extremes. Tallest building, fastest vehicle, deepest dive. These comparisons frame progress as competition. But the deep ocean reveals the limits of that framing. No building approaches the depth of trenches. No vehicle can operate freely there. Our deepest dives are brief and rare. The environment remains largely unaffected by these milestones. In this context, human achievement feels less like conquest and more like careful borrowing. We borrow moments, we borrow data, we borrow glimpses, then we retreat. This dynamic reshapes the narrative of exploration. Instead of triumph, there is observation. Instead of dominance, there is respect. Instead of certainty, there is curiosity tempered by caution. The deep ocean humbles us not by denying access entirely, but by offering just enough access to reveal how much remains beyond reach. That balance is important. Complete inaccessibility might be ignored. Complete accessibility might lead to exploitation. Partial access creates awareness without illusion of control. The Hadal zone occupies that space. It reminds us that Earth is still larger than our systems, that complexity exceeds our frameworks, that life adapts in ways that do not prioritize visibility or relevance to human concerns. This humility has implications beyond oceanography. It influences how we think about life elsewhere, about extreme environments, about what is necessary for survival. It tempers assumptions about habitability, exploration, and discovery. If life can persist quietly under kilometers of water, without warmth or light, then the absence of familiar conditions does not imply absence of life. It implies difference. And if entire ecosystems can exist largely outside our awareness, then knowledge itself becomes a partial map rather than a complete picture. This perspective does not diminish human curiosity. It refines it. Curiosity becomes less about ownership and more about listening, less about reaching the end and more about understanding boundaries. As attention lingers on this humility, one final realization begins to form, not about limits alone, but about what remains unresolved. About the fact that even after all observation, all technology, and all reflection, the deepest parts of the ocean still hold something back. Not as a challenge, not as a secret to be unlocked, but as a reminder that some depths keep their distance, quietly, indefinitely. As attention begins to rise from the deepest parts of the ocean, there is a temptation to tie everything together neatly, to summarize what has been learned, to frame the unknown as a problem waiting for a solution, to suggest that with enough time, funding and technology, the Hadal zone will eventually surrender all of its secrets. That impulse is understandable. It is how humans often relate to the unknown. But the deep ocean does not respond well to that framing. The Hadal zone does not keep its secrets because it is mysterious in a dramatic sense. It keeps them because it exists on terms that do not align with human presence, human perception, or human timelines. Its secrecy is not intentional. It is structural. Depth alone creates distance. Pressure enforces exclusion. Darkness limits observation. Cold slows processes. Scarcity reshapes behavior. Together, these conditions form an environment where visibility is the exception, not the rule. Where most activity occurs outside the narrow windows we're able to open. What we have seen so far is real. It is meaningful. It has changed how we understand life, evolution, and the limits of biology. But it is incomplete by necessity. Each glimpse is constrained by the tools we use and the brief moments we're able to spend there. When a lander settles onto the trench floor, its arrival is temporary. Lights come on, cameras record, sensors measure, and then, after a few hours, the lights go out, the ballast releases, and the machine begins its long ascent back toward the surface. Darkness returns, pressure remains, life continues, nothing down there waits. This continuity is important. It means that the deep ocean does not exist in anticipation of discovery. It does not pause for observation. It does not respond to curiosity. Processes unfold regardless of whether they are witnessed. From a human perspective, this can feel unsatisfying. We are accustomed to environments that reveal themselves quickly. Forests can be walked through. Mountains can be climbed. Even space, for all its danger, offers views that are immediate and dramatic. The deep ocean offers none of this. It offers fragments. Those fragments have shown us a world that operates without sunlight, without warmth, without colour, under pressure that defies intuition. They have shown us organisms that are not exceptional by surface standards, but that are precisely aligned with their conditions. Life that persists not by pushing limits, but by avoiding failure. What they have not shown us is everything. Entire trenches remain unvisited, entire slopes unmapped, entire chemical environments unsampled, entire communities unobserved. Not because they are hidden deliberately, but because reaching them requires effort that exceeds our current capacity. Even the trenches that have been visited are known only in pieces, a few hours here, a few samples there. The majority of their volume remains untouched. This unevenness matters. It means that any attempt to describe the Hadal zone as a whole must remain provisional. We can describe patterns, but not totals, tendencies, but not absolutes. Every statement carries an implicit caveat, based on what we have seen so far, and what we have seen so far suggests restraint. There is no evidence of dramatic, large, fast-moving predators waiting in the darkness. Energy constraints make such life unlikely. There is no indication of ecosystems built on abundance or excess. Everything points toward efficiency, conservation, and persistence. The secrets the Hadal zone keeps are not theatrical. They are subtle. They may lie in microbial processes that operate just above the threshold of detection, in metabolic pathways that proceed so slowly they leave faint signatures, in life forms that exist within sediment layers or chemical gradients rather than open water. They may lie in evolutionary histories that diverged long ago and continued in isolation, producing lineages that remain unknown simply because no instrument has passed close enough at the right moment. They may lie in interactions that unfold over years or decades, invisible during short visits, reproductive events triggered by rare conditions, community shifts following geological disturbances, long recoveries from events we do not witness. In many cases, we do not even know what to look for. Exploration often proceeds by refining questions, but those questions are shaped by existing knowledge. The deep ocean challenges this process. It requires methods capable of detecting the unexpected, the quiet, the slow. This does not mean the Hadal zone is unknowable. It means it resists completion. There is a difference between mystery and incompleteness. Mystery implies something hidden that could be revealed with the right key. Incompleteness implies that no single perspective can capture the whole. The Hadal zone is incomplete to us because we are incomplete observers there. This realization carries a certain calm. If every environment were fully known, fully mapped, fully explained, the world would feel smaller. The deep ocean preserves scale. It preserves the idea that Earth still contains processes that do not revolve around us. That preservation has value. It reminds us that knowledge is not the same as ownership, that understanding does not require dominance, that coexistence does not require visibility. In a time when human activity increasingly reaches into every system, the existence of places that remain largely autonomous matters, not because they are untouched, but because they are not easily reshaped. The Hadal zone is not immune to human influence. Pollutants reach it. Climate change affects circulation patterns. Geological processes interact with altered surface conditions. But the pace and nature of change remain largely beyond our immediate control. This separation creates a boundary that is as psychological as it is physical. It forces humility. Not the humility of insignificance, but the humility of proportion, of recognizing where our reach ends. As we think about future exploration, this humility becomes essential. It encourages careful design, ethical consideration, long-term thinking. It discourages assumptions that access implies entitlement. The deep ocean does not need us to explain it. We need it to remind us that explanation has limits. There is also something quietly reassuring in this. In a world saturated with information, constant updates, and immediate visibility, the idea that some places continue without being watched offers relief. It suggests continuity beyond attention, stability beyond narrative. The Hadal zone does not perform, it does not advertise, it does not change to accommodate observation. It exists, and in that existence it challenges how we think about life. Life does not need warmth, it does not need light, it does not need colour, it does not need abundance. It needs compatibility, it needs stability, it needs time. These lessons extend beyond the ocean. They inform how we think about extreme environments elsewhere, about subsurface life, about distant worlds, about the boundaries of habitability. They also inform how we think about ourselves. Human life thrives in narrow conditions. We require specific temperatures, pressures, and resources. Our adaptability is impressive but not unlimited. Recognizing environments where we do not belong does not diminish us. It contextualizes us. The Hadal zone is not a challenge to human achievement. It is a reference point. It shows that Earth is still larger than our systems, that complexity exceeds our frameworks, that persistence does not require attention. As this reflection settles, the descent ends not with answers, but with perspective. There will be future missions, better instruments, longer observations, new discoveries. Some secrets will be clarified, others will be replaced with better questions, but the deepest parts of the ocean will likely never be fully known in the way familiar landscapes are known. Not because of failure, but because of nature. And that is not something to overcome, it is something to recognize. So as the ascent continues, back toward the surface, toward light, sound and warmth, the Hadal zone remains below, unchanged by the journey. It continues to exist in darkness and pressure, quietly supporting life that does not require witnesses. The depths keep their secrets not as a challenge, but as a reminder that some parts of the world are not meant to be resolved, only acknowledged.